Hello and welcome to Sleepy Science. Tonight we'll loosen certainty's knots and wander 30 quiet edges where mind, body, and cosmos softly trade secrets. You'll feel belief nudge biology without a pill, watch distant things agree as if distance forgot itself, and see stormlight ball into patient orbs no textbook fully explains. We'll step beside those who brushed a bright corridor and came back gentler. Compare clocks that disagree between wingtip and satellite, and notice animals, hear the earth before it speaks. We'll sit with healings that outrun our models, visions many people share when the world tilts, and a single brain that acts like two in the same skull. We'll meet dreams that warn and others that solve, choices that seem to lean backward in time, and matter you can't see that still writes the map. We'll test water that breaks the rules, twins that echo across years, and pain felt in places that are gone. We'll watch randomness sway to human weather, brainwaves braid in deep talk, and children name rooms they've never seen. We'll hear new tongues wake from coma, feel hearts in machines, and see talent bloom after injury. Moods retuned by gentle coils, and surgeries that heal by ritual alone. We'll follow a calm companion through danger, a crowd into the same sweet error, tongues clicking rooms into shape, hands finding impossible strength. Violet winds that help wounds remember, and that small second early knowing that asks you to breathe, to notice, and to begin. The placebo effect. Belief can heal without medicine. You've probably swallowed a sugar pill before without knowing it, not because anyone tricked you, but because every real treatment you've ever had came wrapped in expectations, rituals, and the steady voice of someone who believes you can get better. The startling truth is that those expectations are biologically active, and in some conditions they change your symptoms in measurable, testable ways. Here is the gentle beginning. The placebo effect is not thinking yourself well, and it is not a cure-all. It is the brain and body using learned associations and predictions to dial systems up or down, especially pain, fatigue, nausea, and anxiety, when the context signals that relief is on the way. Your nervous system carries a descending pain control network, from the prefrontal cortex through the periaqueductal gray to the spinal cord. When you expect analgesia, that network can release endogenous opioids and other modulators, so fewer pain signals make it to awareness. We know this is a real pharmacology, not imagination, because opioid-blocking drugs like naloxone can blunt placebo analgesia, and dopamine signaling in reward circuits can rise during placebo responses in Parkinson's disease, even when no active drug is given. Conditioning layers on top of expectation. If a cream once contained a local anesthetic, your body can learn cream means numbness, and the next application, chemically inert, still quiets the sensation. Development. The effect is not limited to pills, and its size is shaped by details you might overlook. The color, size, and price of a capsule change what people feel. Sham acupuncture with retractable needles can reduce pain when the ritual is convincing. A fake surgery in which a skin incision is made but no joint repair is performed can yield similar improvements in knee pain to a real procedure, telling us that part of surgical benefit is context, attention, and expectation. Even open-label placebos, patients told honestly, this is an inert pill, but sometimes these still help via mind-body mechanisms, have reduced symptoms in conditions like irritable bowel syndrome and chronic low back pain, likely because the ritual gives the brain permission to deploy its own pharmacy without deception. Crucially, the same mechanism flips. Nocebo responses occur when warnings prime you for harm, raising pain and side effects through anxiety pathways. A change in expectation can make a neutral sensation feel threatening, and the physiology follows suit. This is where ethics matters. How we explain treatments, tone of voice, clarity, warmth, changes outcomes. A clinician who sits, listens, and expresses realistic hope creates a context in which your predictions tilt towards safety and relief. The biology of rapport is not fluff. It's part of the treatment effect. Yet we must hold the line on limits. Placebo effects do not sterilize infections, lower dangerously high potassium, or consistently shrink malignant tumors. They do not replace insulin in type 1 diabetes or antibiotics in sepsis. Their strongest, most reliable domain is symptom modulation and functional improvement. What you feel and how you move, not the eradication of underlying structural disease. And even within symptoms, responses vary. Some people are highly placebo responsive, others hardly at all. Genetic differences in dopamine and opioid receptors, prior experiences, cultural beliefs, and the credibility of the treatment story all shape the outcome. Think of your brain as a prediction engine that constantly compares what I expect to what I sense, then corrects the error. A convincing therapeutic context tells that engine error should drop now, and the brain actively suppresses incoming signals to make experience match expectation. That's why a precise explanation, what a treatment can and cannot do, works better than hype. Clear stories create stable predictions. Exaggerated promises create volatility and disappointment. If you want to use this responsibly, ask practical questions. What is the evidence for this intervention beyond placebo? If the active effect is small, can we safely enhance context, consistent timing, soothing environment, measured reassurance, so that expectations support rather than replace real therapy? Can we avoid nocebo harm by giving honest, balanced side effect information without dramatizing it? In pain clinics, pairing a low dose of an effective drug with a strong ritual, then intermittently replacing doses with inert pills while keeping the ritual, can maintain relief with fewer pharmacologic exposures. A learned sparing strategy that blends neuroscience with prudence. In primary care, a minute of genuine attention, making eye contact, summarizing what you heard, setting a shared plan, often rivals additional testing for patient satisfaction and can improve adherence, which is itself a driver of outcomes. In psychiatry, explaining why a medication takes weeks to work and how early side effects usually fade protects patients from nocebo-driven dropout. And in every field, separating "this will cure you" from "this will likely help you feel and function better while we also treat the cause" keeps hope honest. The ending is quiet but firm. Belief is not magic, it is leverage. It tilts control systems that were always yours. And when aligned with evidence-based care, it can reduce suffering, improve function, and make treatments work better than they otherwise would. If you leave with one lesson, let it be this: context is part of the dose. The story you and your clinician build together is an active ingredient. And using it well doesn't mean abandoning science. It means finally including the part of science that studies you. Quantum entanglement. Instant connection across vast distances. You hear the phrase, instant connection across vast distances, and it sounds like a ghost wire strung through space. But the honest, more interesting story is this. When two quantum objects are prepared together in a very specific way, they stop being fully describable on their own and instead behave like parts of a single shared description, so that when you later test them, no matter how far apart they've drifted, their results line up in patterns that no ordinary, local explanation can reproduce. Begin gently here. Entanglement isn't a secret message flying faster than light, and it isn't telepathy. What's instant is the appearance of coordinated outcomes when you compare notes, not the transfer of a usable signal, and physicists go to painful lengths to rule out every mundane loophole. In these experiments, you create pairs of particles, often photons, whose properties are linked, send them to distant labs, and choose measurement settings at the last moment using random number generators. When the data are brought together, the correlations violate bounds that any theory of prearranged local instructions would obey. That violation is the landmark. It says your everyday picture, where each particle carries a hidden set of answers that only its own neighborhood can touch, doesn't match how the world actually behaves. Development. You can feel how radical this is by noticing what researchers do to keep the tests clean. They spread the stations kilometers apart, so no light-speed signal could sneak from one to the other in time. They close detection gaps so missed events can't bias the statistics. And they pick measurement angles using unpredictable processes, even starlight from distant galaxies. So no common cause can secretly coordinate the choices. When those precautions still yield the same striking correlations, you learn something sturdy. The universe allows relationships that are stronger than any classical link. yet still refuse to carry messages on demand. That combination, strong but non-communicating, sounds contradictory until you recall that a correlation is not a cable. The pattern only shows up after results are compared, which requires ordinary communication at or below light speed, protecting causality while breaking your intuition. If you want to see how this becomes useful, look at 3 pillars: teleportation, cryptography, and sensing. Quantum teleportation, despite the sci-fi name, does not move a thing from here to there. It uses an entangled pair shared between you and a partner to reconstruct a fragile quantum state at a distance, provided you also send a small amount of classical information. Nothing arrives before that message, and the original is destroyed in the process. But the delicate arrangement of probabilities, what makes the state unique, appears intact on the far side. In quantum key distribution, entanglement allows you to detect eavesdropping. If someone taps the line, the correlations weaken in a measurable way, so you either keep a key that's provably secure or you toss the run and try again. Some protocols even promise security without trusting the devices, because the very statistics of the Bell test certify randomness and privacy. In sensing, you can squeeze uncertainties across many entangled atoms or photons so that a collective measurement of time, acceleration, or magnetic fields beats the normal limits, an advantage that metrology labs are already chasing to sharpen clocks and detectors. The network view makes the story bigger. You can swap entanglement, entangle A with B and B with C, then by a careful joint measurement on B, forge a fresh entanglement between A and C that never met. This is how you stitch long-distance links into a future quantum internet. Quantum repeaters built from memories and swapping stages promise continent-spanning correlations, and satellites have already distributed entangled pairs between ground stations hundreds of kilometers apart. A step toward global systems. If you're wondering why we don't entangle cars or coffee cups, the answer is not that the rules change for big things, but that the environment is nosy. Stray interactions leak information and wash out the delicate connectedness, a process called decoherence. Experiments fight this with ultra-cold temperatures, isolation, and error-correcting tricks, and they have pushed entanglement into larger and larger systems, from clouds of atoms to vibrating membranes and superconducting circuits, showing that fragility is an engineering problem, not a magical boundary. It also helps to see what entanglement is not. 2 matching envelopes with red and blue cards inside can be perfectly correlated, but that's classical. Each card's color is fixed from the start, and learning one simply reveals the other. Entanglement goes beyond that, because the outcomes are not fixed in advance for all the different measurements you might choose. Yet they remain coordinated in a way no hidden instruction set can reproduce, which is exactly what the Bell tests expose. And if your mind reaches for the interpretation question, what is really happening before we look? You're standing at the edge where physics shades into philosophy. Different schools of thought tell different stories about the underlying picture while agreeing on the same experimental facts. Whichever story you like, you can't keep both locality in the everyday sense and a simple realism about preset values without contradicting the data. Here is the soft landing, honest but inviting. Entanglement is not a mystical hotline. It's a resource, a kind of connection nature makes possible that defies common sense while keeping faith with causality. And learning to create, preserve, and convert that resource is quickly becoming an engineering discipline rather than a puzzle in a textbook. You finish this topic with 3 questions to carry forward. How do you tell the difference between a surprising correlation and a usable signal? How do you scale fragile, beautiful links into robust networks that survive the real world? And what picture of separateness are you willing to revise when the most reliable experiments insist that parts of the world sometimes behave, quite literally, as if they were one? Ball lightning, rare plasma orbs. No one can fully explain. A glowing sphere drifts into a darkened room during a thunderstorm, pauses near a window as if curious, then slides away and vanishes with a soft pop. That image sounds like folklore until you realize how many sober eyewitness accounts, pilots, engineers, soldiers, even physicists, describe something like it, and how stubbornly the phenomenon has resisted a clean, repeatable explanation despite centuries of attention. Begin gently. Ball lightning is a label we use for rare, short-lived orbs of luminous gas or plasma, usually the size of a golf ball up to a basketball, lasting a heartbeat to several seconds, often appearing during or just after cloud-to-ground lightning strikes. People report a floating, wandering motion, a quiet hiss or no sound at all, colors from white to orange to green, and sometimes a smell of ozone or burning metal after it disappears. Because such events are unpredictable, science faces a basic challenge. There is almost never time to set up instruments, so the record is dominated by testimonies, scorch marks, and a handful of accidental measurements. Still, the data we do have draw a consistent outline. Many observers say the ball seems to move against a breeze or along walls and wires as if guided, occasionally entering buildings, even appearing to pass through closed windows. Claims that, if not illusions of perspective, hint that the light you see may be the visible face of an invisible structure of air, charge, and electromagnetic fields interacting in complicated ways. Development. Over the years, researchers have proposed a small library of physical mechanisms, each matching some reports while struggling with others, and this is where the story gets both technical and human. One family of ideas starts with the ground itself. When lightning hits soil, it can vaporize silica and other minerals into a hot mist. As that vapor cools and reacts with oxygen, it could form a cloud of tiny particles that continue to glow or burn slowly while electrostatic forces hold them together, a kind of self-sustaining aerosol that looks like a ball and drifts until the chemistry runs out. In lab settings, striking certain substrates with arcs has indeed produced luminous, floating balls a few centimeters across that persist longer than a spark should, lending cautious support to the vaporized silicon root, though scaling that up to a robust atmosphere explanation remains hard. Another path treats the sphere as a microwave trap. A lightning stroke might act like a natural generator of very high-frequency radiation. In the right geometry, a pocket of ionized air surrounded by denser, cooler layers. Those waves could bounce inside like sound in a resonant room, keeping the interior ionized and bright for a surprising length of time. The outer shell would act like a mirror for the microwaves, so the structure would be self-confined until a small disturbance collapses it. That helps explain why some balls seem to pass near conducting surfaces, along wires or cluster around metal objects, and why they sometimes end with a bang. Release the trapped energy and you get a sharp flash and pressure pulse. A third class of models points to thin plasmas sustained by energy drawn from electric fields that linger after a strike. The atmosphere is not electrically neutral in a thunderstorm, and charge layers can feed a localized glow, particularly near sharp edges and wet surfaces where fields concentrate. In this view, the ball is a moving balance between energy input and radiation loss, steered by gradients that are invisible to the eye, but real enough to tug the glowing pocket through a room. What about the most controversial reports? The ball passing through glass. The honest answer is that we do not have definitive evidence of matter walking through a solid window. More plausible is that a microwave-like energy pulse couples through the glass and reignites air on the far side, giving the impression of clean passage, or that observers misjudge trajectories during a startling, fast event. There are, however, documented cases where the sphere leaves circular scorch patterns, melts small areas of metal, or shatters glass outward as if a pressure surge occurred. These physical residues remind us we are not only passing stories, we are trying to match heat, force, and chemical change with a mechanism. Aviation has added valuable clues. Crews have reported luminous balls entering aircraft cabins during storms. Again, entering likely means forming inside after an electrical discharge rides in on wiring or through a pressure equalization pathway, and searing exits that leave neatly punched holes. The repeating features across many accounts hint that ball lightning is not one thing, but a small set of related phenomena that need different boxes on the same shelf. On the experimental front, researchers have generated ball-like glows with microwaves in special cavities, with high current arcs over certain materials, and even with focused electric discharges in salty water mists. These artificial cousins never capture every trait at once, but they show that stable, free-floating luminous structures can exist for seconds when energy, matter, and geometry line up just so. It is equally important to say what ball lightning is not. It is not a wandering sun. It does not violate conservation laws. And the most exotic claims, intelligent motion, sharp turns against wind, silent passage through thick walls, likely wrap real physics in layers of shock and storytelling. Yet the core mystery remains productive because it teaches a method. When nature offers rare events, you build a catalogue, look for recurring signatures, and test the simplest mechanisms that can reproduce them. You respect eyewitness clarity, and you also weigh how stress distorts perception. You build tabletop versions that capture a few features each, then try to stitch them. For practical life, there are calm takeaways. During severe storms, avoid standing close to exposed conductors and metal frameworks. Do not cluster near windows in the hope of a view. And remember that most ball lightning stories end harmlessly, but a few end with damage or injury. Rare is not the same as safe. The soft landing is this. Ball lightning, if you strip away the folklore, is a reminder that our planet still hosts frontier physics on a human scale, where chemistry, weather, and electromagnetism meet in messy, beautiful ways. You do not need a miracle to explain a glowing sphere. You need patience, creative experiments, and a willingness to let multiple mechanisms share the stage until one day a storm, a camera, and a prepared mind give us the decisive record that turns a stubborn wonder into an understood chapter of the sky. Near-death experiences, recurring patterns across cultures. You don't plan the moment when everything narrows and the ordinary world thins to a bright edge, but across ICUs, operating rooms, riverbanks, and roadside rescues, people who have come close to dying report patterns so eerily familiar. Tunnels of light, a sudden quiet, leaving the body and looking back, a compressed life review, meeting helpful figures, that it tempts you to think there is one script playing everywhere. The more careful, and to me more interesting, truth is that there are repeated motifs shaped by biology and then colored by culture, and studying them has taught us surprising things about both the human brain and the human need for meaning. Begin gently. Clinicians have collected thousands of accounts and used structured questionnaires to code them. How vivid, how coherent, which features occurred, and common threads do appear regardless of age or language. An overwhelming sense of peace, time slowing or vanishing, a bright region that feels like a destination, the idea of crossing a boundary and then being sent back. Yet when you look closer, the scenery varies with the life you've lived. A border may be a river, a gate, a bridge, or a line in the sand. The presence may resemble a loved relative, a religious figure, or a neutral guide. Children often report simple scenes instead of moral reckonings. People raised without strong spiritual stories still describe clarity and connection, but with less elaborate characters. That cultural tinting tells you these experiences aren't simple recordings of a single external place. They are constructed with materials the mind already holds, and the construction happens under extreme physiological stress. Development. What is the brain doing at those thresholds? Several well-supported mechanisms can produce pieces of the NDE mosaic. When blood oxygen falls and carbon dioxide rises, during cardiac arrest, drowning, or massive blood loss, vision often collapses inward to a tunnel because the retina and visual cortex do not fail evenly. Peripheral processing is more vulnerable, leaving a bright center, and pilots undergoing high-G training describe grayouts and tunnel vision for the same reason. The temporal and parietal regions, especially near the temporoparietal junction, integrate signals about where you are in space. Electrical stimulation there can evoke the sensation of rising above your body or floating near the ceiling. And certain migraines and seizures produce similar out-of-body illusions. Evidence that I am here is a brain-made map that can be temporarily redrawn. Panic is not the only chemistry in play. The body dumps pain-dampening opioids and other modulators during trauma, and many report a surprising calm or euphoria. Some anesthetics and dissociative drugs, when administered in operating rooms or sampled in studies, can reproduce NDE-like features, a sense of detachment, bright scenes, helping figures, a re-evaluation of life priorities afterward. Sleep systems sometimes intrude as well. Elements of REM sleep can appear at the wrong time under stress, blending waking awareness with dreamlike imagery. paralyzing the body while leaving the mind alert. One reason some NDEs feel astonishingly real and embodied. And at the very end, a brain that looks quiet at the bedside may still produce brief storms of organized activity. Recordings in animals after cardiac arrest and rare human cases near death show bursts of coherent rhythms and crosstalk across distant regions, as if a final, high-energy wave passes through networks that usually support perception and memory. That doesn't tell you what the content is, but it shows the machinery can briefly surge when the heart stops, giving a plausible window for intense experience and the laying down of lasting memories. This biophysiology does not cancel the mystery people feel. It explains how such experiences can be vivid, structured, and unforgettable, without requiring the brain to be either fully on or fully off. What about the strongest claims, the ones that say the person saw details they could not have seen? Numbers on a machine, a phrase spoken in another room. Researchers have tried prospective tests, placing hidden images in resuscitation areas and interviewing survivors quickly. The results so far are sparse and mixed. Most survivors don't recall anything. Some recall experiences without verifiable elements, and very few report details that can be checked, with even fewer meeting strict standards for timing and accuracy. That doesn't mean every story is mistaken. It means the best available data neither confirms nor rules out unusual perception, and it pushes the field toward better designs, independent time markers, multiple observers, and consistent interviewing protocols that minimize suggestion. Meanwhile, there are practical, humane lessons that don't depend on solving metaphysics. Many who return describe a durable shift in values, greater empathy, less fear of death, renewed commitment to relationships. Clinically, that suggests follow-up care should include space to process meaning, not only bodily recovery. For resuscitation teams, the possibility that people sometimes have awareness during CPR, even if rare, has inspired training that emphasizes respectful talk at the bedside and reduces sensory chaos. It costs little to assume someone might hear you and to act with dignity. In palliative care, understanding that the brain can generate peaceful, structured end-of-life imagery helps families worry less about delirium. When a patient describes radiant visitors or beautiful places, the goal becomes comfort and companionship rather than correction. And for science itself, NDEs are a discipline in humility. They remind us that consciousness is capable of integrated, meaningful experience under conditions we too easily label unconscious, and that first-person reports, while fallible, can point toward mechanisms worth testing. The soft landing is careful and open. You don't have to choose between scoffing and surrendering. You can hold two ideas at once: that the brain has known ways to produce the major elements of near-death narratives, and that these experiences matter deeply to the people who have them, reshaping lives in ways we can measure. If you carry anything forward, let it be a better question, not a harder answer. What do these recurring patterns say about the way your mind builds a world? How might that knowledge help us ease suffering at the edge of life? And what kind of listening would honor both the biology and the meaning when someone says, simply, "I saw a light and I came back"? Time dilation, observed in airplanes and GPS satellites. You don't feel it when you board a plane or check a map, but the clocks you trust quietly disagree about how much time has passed. And if you want your phone to put your blue dot on the right sidewalk, entire systems are built to manage that disagreement on purpose. This is where you learn that time is not a universal drumbeat, but a pace that depends on motion and height. And the proof isn't thought experiment theatre, but hardware flying over your head and riding under your seat. Begin gently. Half a century ago, physicists flew ultra-stable atomic clocks on commercial airliners and compared them with matching clocks left on the ground. The flying clocks lost a tiny slice of time while moving eastward and gained a little. Going westward, exactly as predicted when you account for two effects. Time runs slightly slower for objects in motion and slightly faster higher up where gravity's pull is weaker. The differences were only tens of nanoseconds, a few billionths of a second, but the sign and size matched what the theory said they should be when you add both motion and altitude. And that's the point. You can't explain the data with speed alone or height alone. The world makes you keep both in your head at once. Those airplane tests were crude by today's standards, but their spirit lives in every navigation fix your phone makes using satellites. Each satellite in the GPS constellation carries atomic clocks and broadcasts a running timestamp along with its exact position. Your receiver listens to several at once and works out how far each signal traveled by noting how late it arrived. Because light covers roughly 30 centimeters in a billionth of a second, even a small timing slip throws your location off by the width of a lane. To keep you on the right street, the system has to keep timing honest to within a few billionths of a second, day after day. Here's the twist you wouldn't guess without looking. The satellite clocks do not tick at ground pace. They are high above Earth, about 20,000 kilometers up, so their altitude makes them run faster than ground clocks, while their orbital speed makes them run slower than if they were parked. The altitude effect is bigger, so the net result is that a satellite's onboard clock would surge ahead of a ground clock by a few dozen microseconds each day if you did nothing. That may sound trivial, but multiply that by the speed of light, and you get errors that would smear your location by kilometers in minutes. So the designers didn't just launch clocks and shrug. They pre-offset the satellites so that once in orbit, after both effects take hold, the tick rate as seen from Earth matches the ground standard. On top of that, the control segment continuously monitors all the spaceborne clocks from tracking stations around the globe and uploads small corrections because tiny drifts, thermal cycles, and magnetic influences still nudge even superb devices. There's more hidden craft. Your receiver also accounts for the Earth's rotation, while signals cross the sky so that eastbound and westbound paths don't introduce a subtle twist. It estimates delays through the ionosphere, which bends and slows radio waves depending on electron density. By comparing two different broadcast frequencies, it adjusts for the troposphere's humidity and pressure. It even folds in small relativistic tweaks when a satellite's orbit stretches or compresses slightly so the clock speed shifts with altitude during each lap. None of this is speculative. It is written into the engineering because without it, the system would drift uselessly. If you want a feel for scale, imagine two identical clocks, one on a high mountain and one at sea level. The one higher up runs a hair faster just by being farther from Earth's center, and modern optical clocks are so sensitive that lifting one by a single floor in a building produces a measurable difference. Labs now move suitcase-sized optical clocks between cities by car and measure the time gained and lost over a drive with such precision that elevation profiles leave a fingerprint in the data. In other experiments, two clocks sit on different shelves and tick at measurably different rates, simply because one is about a meter higher than the other. These aren't parlor tricks. They're direct statements that how fast time flows is not a property you can assign without asking, according to whom and where. If the airplane story launched the idea and the satellite network made it practical, the new generation of timekeepers is turning it into a tool. Physicists use arrays of atoms trapped in light to build clocks so quiet and steady that they can listen to gravity itself. In the near future, timekeeping will map small changes in the planet's mass distribution, water moving underground, ice sheets thinning, because shifts in gravity slightly retune the local tempo of time. You should pause on how strange and ordinary this has become. Your navigation app, which to you is a simple arrow and a street name, can only exist because someone, somewhere, is constantly reconciling many versions of now that don't quite agree. The conclusion is not mystical, it's practical and a little humbling. Time dilation is not a distant curiosity, it is a daily correction woven into global infrastructure, made visible by instruments that discipline our intuition. The honest takeaway is threefold. First, motion and altitude both matter, and they push in opposite directions. Airplanes teach you to add them with care. Satellites prove you must. Neither effect can be ignored if you want accuracy. Second, the precision of modern clocks has made relativity a tool rather than an anecdote. Engineers don't debate whether it's real, they budget for it. Third, your sense that A second is a second everywhere is a useful shortcut for living, but a poor guide for measuring. If you change your path or your height, you change your pace through time. Ask yourself, as a way to keep learning, what other everyday technologies hide hard-won insights about the world? What other constants do we treat as given until better instruments reveal their subtle dependence on context? And when you hold that phone and watch your dot glide down the street, can you feel, just a little, the quiet choreography that keeps a handful of clocks in the sky and a handful on the ground in just the right kind of disagreement so that you, down here, can know where you are? Animals sensing earthquakes before they happen. A courtyard erupts before the ground does. Dogs whining at closed doors, chickens flapping into trees, a snake streaking from a stone wall. As if the neighborhood received a message you didn't. And the sober question isn't, do animals have a sixth sense? But, what real signals are available to a body that's lower to the ground, more finely tuned, and living closer to the weather of the earth? Begin gently. Many reports of animals predicting quakes are anecdotes remembered after the fact, but scattered among them are patterns that line up with physics. The planet often whispers before it shouts, and other creatures are better listeners. The most straightforward whisper is mechanical. When a fault finally slips, it releases two main families of seismic waves, and the first to arrive, the fast, small amplitude compressional waves, can reach you seconds to tens of seconds before the stronger, more damaging waves that make books jump and walls sway. Humans rarely notice that first ripple, but animals with sensitive inner ears, whiskers, or ground contact do. Fish and amphibians feel pressure changes and subtle vibrations through lateral lines and skin. Burrowing animals live inside the medium, and even household pets may respond to the faintest floor shiver long before you label it earthquake. In this narrow sense, before it happens often means before you consciously notice, and that alone could explain frantic movements moments ahead of the obvious shaking. Development. The truly tempting idea is that some animals react not just seconds early, but minutes or hours or days, and here the evidence is mixed, fascinating and fraught. There are claims of toads abandoning ponds days before a European quake, goats on a volcano's flank growing restless hours before a swarm, cows pacing, and dogs barking in coordinated bursts the night before a shock. Critics counter that animals do unusual things all the time, and in a world full of quakes, some coincidences will look meaningful by chance. To sort signal from story, researchers have strapped tiny accelerometers and GPS units to farm animals and wildlife, then compared movement bursts to local seismic catalogues. In some cases, bursts cluster within specific windows before nearby quakes more often than you'd expect randomly, suggesting that groups can act like amplifiers. One animal startles, another mirrors, and a farm becomes a sensor array. What could they be responding to if not the first arriving waves? Several plausible testable candidates exist. Rock under stress can crackle, as tiny fractures open and close. They emit high-frequency vibrations and infrasound too low for you to hear, but not for an elephant or a dog. Grinding minerals can also release electrical charges and ionize air near the ground. Changes in local electric fields may tickle whiskers and skin. And there are lab studies showing insects and small mammals alter behavior when exposed to sudden field shifts. Underground fluids shift as fractures dilate. Groundwater chemistry changes. Gases like radon and ozone burble along new paths. And odors or dissolved irritants could make a pond suddenly unfriendly to a toad, long before a human detects anything unusual. In coastal zones, pressure waves travel through water faster and cleaner than through layered rock, giving marine life a longer runway to react. None of these mechanisms requires magic. Each is a real pathway from stressed crust to a sensitive nervous system. The problem is not possibility, it's proof. Nature is noisy, behavior is variable, and earthquakes are rare at any one place, so it's easy to overfit a story to a small dataset. This is why the most credible projects treat animals like instruments. They define what counts as an alarm in advance, log continuously for months, and resist the urge to reinterpret criteria after a quake. They look for spatial patterns. Do farms closer to the eventual epicenter move first, with distant herds responding later? And temporal patterns. Does activity ramp as the clock ticks toward the main shock, then drop? That would be hard to fake by random noise. They also compare species. A dog and a cow have very different sensors. If both spike together, it hints at a shared external cause rather than idiosyncratic stress. Meanwhile, we shouldn't neglect the simplest channel of all: social contagion. One skittish goat bolts at a faint tremor or sudden static snap, and the whole herd surges. One dog's bark startles a row of others. What looks like mass premonition can be networked startle, powered by loud evolved priorities. Move first, ask later, that keep prey alive. Where does this leave you practically? Early warning systems already use instruments to catch the fast waves and broadcast alerts before the damaging waves arrive. Animals, if they truly add lead time, would have to outperform precise machines that sit on the fault day and night. That is unlikely in urban settings, but a hybrid approach could help in rural regions where instruments are sparse. A collar network on farm animals streaming motion data could feed into the same algorithms that digest voltages and ground velocities, flagging unusual synchronized activity across many species as a soft precursor that deserves attention, then letting the hard physics confirm or dismiss it. For now, 3 ideas are worth carrying. First, seconds matter. If you train yourself to act on a phone alert or on your own pet's sudden panic during a tremor, you win the only currency earthquakes offer. Second, humility helps. Animals clearly detect some signals you miss, but many stories will be false alarms, and designing good tests means loving negative results as much as dramatic ones. Third, curiosity is not superstition when it leads to measurement. If a village's fishermen report eels surging from the riverbed the evening before nearby shocks, the right response is not to scoff or to canonize the tale, but to wire the river, log the eels, and see what the numbers say over a year. The soft landing is this: animals don't read the future. They live closer to the present than we do, with bodies that register shivers in stone, breaths in water, and charges in air we've learned to ignore. Whether or not they'll ever help us forecast a quake days ahead, they already teach the discipline of listening, of watching the edge of awareness where warning first appears. And in a world where the ground can change its mind without notice, that kind of listening is its own kind of safety. Spontaneous remission. Cancer disappearing without treatment. A rumor travels through hospitals like a dare. Someone's scans cleared without chemotherapy. A tumor shrank after months of waiting. A biopsy-proven cancer faded on its own. And because hope is heavy and rumors are light, the only honest way to begin is this: spontaneous remission is real but extraordinarily rare. A documented edge case that has taught medicine surprising lessons about the body's defenses, tumor biology, and our limits of certainty. And if you carry anything away, it should be not a promise, but a clearer map of what might be happening when the improbable occurs. First, terms matter. Clinicians distinguish partial regression from complete remission and demand hard evidence. Imaging that can be compared. Pathology reviewed by expert eyes, and follow-up that lasts longer than a news cycle, because 2 common pitfalls haunt the story: misclassification and overdiagnosis. With those sober filters in place, real cases remain, and they cluster in a few diagnoses. In infants with certain neuroblastomas, a subset can mature into a harmless form or regress. In melanomas, renal cell carcinoma, and some lymphomas, the literature records tumors shrinking without active therapy. Hepatocellular carcinoma and a handful of leukemias have rare reports as well. The most compelling thread through these cases is the immune system waking up. For over a century, physicians have noticed that infections sometimes precede unexpected tumor regression. William Coley, a surgeon in the 1890s, injected bacterial toxins into patients after observing one man's sarcoma recede following erysipelas. And while his methods were crude and risky, the intuition that feverish immune activation can tip the balance seeded ideas that matured into modern immunotherapy. Today, we know tumors are not invisible. They shed abnormal proteins that T cells can recognize. Yet cancers survive by learning to muffle danger signals, recruit regulatory cells, and up-regulate checkpoints, molecular breaks that tell immune soldiers to stand down. Occasionally, An infection or strong inflammatory event resets that balance. Danger alarms surge, the brakes slip, and quiet T cells turn militant, infiltrating the tumor and sometimes rippling through metastases as well. A related clue comes from pathology reports describing tumor-infiltrating lymphocytes, clusters of immune cells inside the tumor microenvironment, correlating with a higher chance of regression. Their presence doesn't guarantee victory, but it shows the fight is joined. Other mechanisms whisper from case to case. Tumor blood supply, a rickety network of new vessels, can collapse. When that scaffolding fails, a mass starves from its center outward. Hormonal shifts can rob certain cancers of a signal they depend on, as occurs in some thyroid and gestational tumors. Abrupt changes in the body's terrain, pregnancy ending, endocrine therapy stopping or starting, have coincided with regressions that look less like magic and more like ecology. Tumor cells themselves are not immortal masterminds. They carry mutational burdens that sometimes become too heavy, triggering internal death programs when a key safeguard breaks, especially in growths that have outpaced the support of surrounding tissue. There is also a quieter phenomenon called dormancy. Small clusters of malignant cells can survive in a kind of frozen standoff, restrained by immune surveillance and starved by poor vascularization. For years, they neither progress nor vanish, and in rare cases, that stalemate ends with the host winning, not by a single dramatic strike, but by many small defeats accumulating inside the enemy camp. The difference between these biological stories and wishful thinking is that they point to testable consequences. And indeed, modern oncology has turned lessons from spontaneous remission into tools rather than legends. Checkpoint inhibitors, drugs that release the immune system's brakes, have produced durable remissions in cancers once considered relentless. Oncolytic viruses are engineered to infect and burst tumor cells while waving danger flags to the immune system. Bacterial vaccines are being revisited under controlled conditions to safely mimic the immune awakenings that old case reports hint at. Radiotherapy sometimes triggers an abscopal response, where irradiating one tumor stirs immune activity that shrinks others not directly treated, suggesting a way to combine precision killing with systemic alarm. None of this makes a plan out of a miracle. The base rate is unforgiving, and choosing to wait for regression in a dangerous cancer is not prudent medicine. The practical, humane guidance is this. If you ever hear the words spontaneous remission, ask for documentation and timelines, not headlines. Insist on second reads of pathology slides for hard-to-classify tumors. Learn whether your cancer type has any recorded history of regression and under what circumstances. If a credible regression occurs, work with your team to enter a registry or study, because rare successes only become knowledge when they're counted. Conversely, if you are weighing treatment, ask how modern therapies already harness the same biology that makes rare remissions possible. Is there an immunotherapy trial suited to your tumor's specific markers? Would a combination of local therapy and immune activation increase the chance of durable control? What lifestyle choices, sleep, movement, infection prevention, won't cure a tumor but will support immunity and resilience during therapy? The conclusion is careful and still hopeful. Cancer disappearing without treatment is a reminder that the body is not a passive battlefield. It is an active province with patrols, alarms, and repair crews. Sometimes those patrols get the upper hand without our help, and from those exceptions, we've learned strategies that now save ordinary lives on purpose. If you want a better question then, will this happen to me? Try this. What does this rare victory reveal about how defense and disease negotiate inside a person like me? And how can my care use that negotiation to my advantage? In that reframed light, spontaneous remission is not a loophole to chase. It's a signpost pointing toward therapies that make the improbable, an immune system that truly sees and clears, a little less rare, and toward a style of medicine that honors both numbers and stories while never confusing them. People seeing the same hallucination during shared trauma. A scream in the dark is contagious, but what takes your breath away is when people later describe seeing the same impossible thing. A figure in the doorway, a wave of insects on the wall, a face at the window, down to the color of the eyes and the angle of the head, as if trauma had tuned them to a single channel. The careful way to begin is to say that shared hallucinations are not proof that something external was there. They are proof that under pressure, multiple minds can be driven by the same cues, the same expectations, and the same biology to build the same picture at once. Start with the mechanics of a crisis. When fear spikes, your body floods with stress hormones, vision narrows, hearing sharpens in jagged bursts, and your brain shifts from careful analysis to rapid guesswork. In that mode, the mind leans heavily on prior stories. What would be dangerous here? What shape would threat take? What pattern should I complete? And when several people share the same prior, their guesses converge. Add the setting: low light, flickering shadows, sirens reverberating through windows, dust or smoke that gives every light a halo. And your senses deliver ambiguous data that multiple observers resolve the same way, because they're standing in the same ambiguity. This is not mystical. It is predictive perception doing its job under extreme constraints, and social influence acting as a fast consensus engine. Someone gasps, "There's a man," and your brain, eager to be on the same page, locks onto man-shaped edges in the noise. Development deepens with what trauma does over minutes and hours. People hyperventilate, carbon dioxide drops, causing tingling, dizziness, and a sense of unreality that itself invites unusual interpretations. Rooms fill with fumes from damaged heaters or generators. Low, undetected levels of carbon monoxide degrade oxygen delivery to the brain. And entire families report similar visions and sounds until the gas is cleared. An environmental cause masquerading as a mental contagion. Vibrations from heavy machinery or distant thunder produce infrasound below your conscious. Hearing yet able to nudge anxiety and make objects hum, and a crowd under that invisible pressure can feel a presence and fill it with shared content. Add sleep debt from a long rescue shift or a night of sirens, and people slip into micro-dreams that leak into waking experience. Once one person names the intruder in the doorway, others' half-formed images harden into the same form. After the event, memory cements through conversation. Co-witnesses align their details without meaning to. A phenomenon known as memory conformity. Small differences iron themselves out in the retelling until the group produces a crisp, unified account that feels truer because it is shared. Psychiatrists see a more intimate version in induced experiences, where a dominant person's firm belief is gradually adopted by a close partner, two people, one delusional architecture, and responders at disasters see a faster, wider cousin when fear, rumor, and suggestion rush through a crowd. None of this means people are weak or gullible. It means that in danger, survival favors synchronized guessing. To keep the inquiry honest, it helps to separate three classes of cases that often get mixed. First, are true near-simultaneous illusions during acute stress. Many people in the same volatile environment making the same perceptual leap. Second, are environmental poisoning or physiological stressors. Gas leaks, mold, heat, dehydration, pushing multiple brains in the same odd direction at once. Third are post-event reconstructions that grow more similar with each conversation. Each class asks for different tools. For the first, you want fast, independent accounts taken separately, with careful timelines and minimal leading language. For the second, you want air monitors, blood levels, and building inspections. For the third, you want to capture the earliest version of each memory before the group sands off the edges. There are also quieter, more intimate versions of shared, seeing that follow grief or extreme isolation. Bereaved spouses sometimes report vivid visits from the deceased, and while those experiences are typically individual, groups in a vigil can describe parallel imagery. Warmth in the room, a figure by the door, drawn from the same emotional vocabulary. Mountaineers trapped in storms report a third companion who encourages them, and teams speak of it together afterward. In those settings, the mind is doing care work, not deception. Generating a guide when a guide would be useful, and the group gives it a name. But trauma can also seed organized false alarms in public. A bad smell in a school, a few students fainting, and suddenly dozens feel chest tightness and dizziness, all real sensations born of anxiety and mimicry. The right response in those cases is calm evacuation, medical checks to rule out toxins, and careful communication that lowers arousal without dismissing pain. If you're looking for controlled science rather than anecdotes, Psychologists have shown in laboratories that people can be nudged to see the same non-existent object when primed with the same story or the same ambiguous picture. Co-witness experiments show how quickly two observers' memories align after just minutes of discussion. Sleep researchers show how deprivation boosts the intrusion of vivid imagery into waking, and hazard teams document entire households reporting identical footsteps, voices, and figures until a carbon monoxide alarm finally chirps. What do you do with this knowledge in real life? Build protocols that respect experience while protecting truth. In a shelter or emergency room, you take reports one by one with open-ended prompts. In search and rescue, you forbid speculative labels over the radio until a target is confirmed, because gunmen and gas leak drive very different group pictures. In homes and schools, you keep detectors maintained and pay serious attention to subtle symptoms that cluster across people. Headache, nausea, confusion, which point to the air, not the soul. And in all these spaces, you teach teams to expect convergence. If 5 people give the same striking detail verbatim, that could mean accuracy, or it could mean they shared a story. What breaks the tie is independent timing, physical traces, and the consistency of peripheral details that social influence usually cannot invent in unison. The soft landing is neither cynical nor credulous. A shared hallucination is a human event, not a supernatural one, and it carries 2 simultaneous lessons worth holding. First, in a crisis, your perception is a negotiation between the world, your body, and the group. Strengthening any of those threads, better lighting, cleaner air, calmer communication, makes the picture truer. Second, meaning matters. People who have seen something together, even if it was born inside, are telling you about their fear, their values, and their need for coherence. The ethical response is to investigate causes with instruments and to respond to people with care. If you leave with one skill, let it be this. When many voices insist on the same impossible sight, listen carefully to the witness and then to the room itself. The hum of the building, the draft from the vent, the chemistry of the air, the stories that were already in circulation. And you'll often find that what looked like one eerie vision was a chorus, each voice carrying a different note from the environment, the body, and the mind, all aligning for a moment under pressure into a single, unforgettable picture. Split-brain patients acting like 2 separate people. A single body walks into the lab and then, with a few careful tricks of light, behaves as if 2 minds lived inside it. That sounds like a riddle until you see how neurosurgeons once treated catastrophic epilepsy by cutting the largest bridge between the brain's hemispheres, and how psychologists learn to speak to each half almost privately, revealing a quiet division of labor that normally stays hidden. Begin gently. The operation, callosotomy, severs the corpus callosum, the thick tract that lets left and right hemispheres exchange information. Patients usually wake with the same personality and conversational skills they had before, which is why the phenomenon went unnoticed until experiments isolated what each half could see and control. Because the optic nerves cross and the visual fields split, researchers could flash an image to only the left or right side of your gaze for a fraction of a second, too fast to move your eyes, and then ask you to respond with a hand the opposite hemisphere controls. Show a key to the left visual field and your right hemisphere sees it. Your left hand can reach under a curtain and pick up a key by touch. Yet when asked, "What did you see?" your voice, mostly a left hemisphere talent, often answers nothing or names a different object cued by what the right hand is holding. Reverse the setup and a word sent to the right visual field is reported fluently, while the left hand gropes without guidance. Development opens wider when you probe functions beyond naming. The right hemisphere, though often quieter with words, can match faces, read simple emotions, and even obey written commands flashed to its field. A patient might chuckle or stand up, then offer a plausible but invented reason when the experimenter asks why. "I was cold," says the left hemisphere's interpreter, building a neat explanation after the fact to keep the story of self coherent. This habit of confabulation is not deceit. It's the brain's default. When internal channels fall silent, the narrator stitches the patchwork anyway. In more dramatic cases, the 2 sides pull in different directions, literally. A shirt buttoned by the right hand may be unbuttoned by the left. One hand grabs an object the other tries to put down. Clinicians call the rarest and most striking version alien hand, where a limb performs goal-directed actions that the speaking self disowns. You can watch purpose emerge without a single central conductor. Each hemisphere has motives and maps, and when they can't negotiate, the body becomes the arena where impulses compete. None of this means the person is two people in the everyday sense. Most of the time, life runs smoothly because the world keeps both halves in sync. Both eyes see the same scene. Both ears hear the same voice. Both hands work on the same task. And because many pathways other than the main bridge still connect structures deep in the brain, but the lab can pry them apart just enough to show specialization you never notice in a fused mind. Language is usually anchored left, but this is a tendency, not a law. Some right hemispheres can name simple pictures, and some left hemispheres read faces well enough to challenge old stereotypes. Numerical processing and fine sequencing skew left. Spatial construction and global shape recognition skew right. Music splits into strands. Melody and spatial layout to the right. Rhythm and counting to the left. Yet practice and plasticity can tilt the balance. What makes the split brain story more than a curiosity is what it says about the self you take for granted. First, your sense of unity is an achievement, not a given. It is built from parallel specialists exchanging compressed summaries. And when the bridge goes, the summaries cannot travel. So islands of competence act alone. Second, your experience is narrated. The interpreter in the language-dominant side keeps a running account of why you did what you did, and why the world looks the way it does. And when the real causes are hidden, it chooses sensible fictions over silence, the way a news anchor keeps talking over a dead feed. Third, will is layered. Urges, habits, and plans can disagree within one skull, and coordination, not domination, is the healthy norm. Clinically, the operation succeeded. For many people with brutal seizures, cutting the bridge reduced storms that no drug could tame, allowing careers, families, and quiet nights. The price was subtle and mostly visible only under contrived tests. Ethically, the work taught restraint. Experimenters learned to ask politely of each hemisphere and to debrief patients about odd lab experiences without imposing metaphysical claims they never endorsed. Technologically, the findings seeded new tools. Modern brain-computer interfaces exploit the fact that a hemisphere can act on information you cannot verbalize, and rehabilitation harnesses cross-cueing, using one hand to write a hint the speaking side can read, to work around blind spots. Philosophically, the lesson is not that you harbor two souls, but that personhood is a network property emergent from cooperation. Your unity is robust in daily life, yet fragile under surgical isolation. Like two musicians who can keep time together while they can hear each other, but slide into independent tempos if the monitors fail. The soft landing is clear and provocative at once. Split brain research does not dissolve the self. It makes the self visible as a process, prediction, negotiation, narrative, and compromise, running on a pair of hemispheres with different talents. And if you take one question forward, let it be how you might listen for your own quiet splits. The hand that reaches while your mouth hesitates. The tug toward a choice your story can't yet explain. And build better bridges on purpose. Not with anatomy, but with habits that let your specialists compare notes before the body moves. Dreams, predicting real-life events in documented cases. You wake with your heart sprinting, and a scene so crisp it feels borrowed from tomorrow. A bridge closed by flashing trucks, a friend in a blue jacket crying at a station, a date on a page, and then, hours or days later, the real world appears to rhyme with what you saw. The honest way to begin is not by declaring prophecy, but by asking how often minds rehearse possibilities at night, how we record those rehearsals, and why a few end up matching events closely enough to unsettle even careful skeptics. Dreams are not random noise. During rapid eye movement sleep, your brain replays fragments of recent experience, mixes in older memories, and runs loose simulations of what could happen next. The way a weather model runs many storms to see which path is plausible, because waking life also spins on patterns, workflows at the office, habits in relationships, cycles in markets. A dream that guesses the next link in a chain is not impossible, just usually unremarked because the hit is partial or the timing fuzzy. The stories that stick in culture are the sharp ones. A writer dreams a specific headline. A commuter sees a crash with a name and mile marker. A scientist sketches an apparatus that later works. You can line up famous cases. The Welsh coal tip collapse preceded by children's dreams. The Victorian premonitions that filled pamphlets. The quiet entries in personal diaries where a symbol later matches a funeral program. But if you want to avoid fooling yourself, you must also count the ocean of misses, the similar but not quite matches, and the edits memory performs after the fact. This is where method matters. Retrospective testimony, I dreamt it, then it happened, is vulnerable to selection bias, confirmation bias, and memory conformity. Prospective recording changes the game. Keep a daily dream log with timestamps made before you know the news of the day. Write in plain language, no hedging after the fact. Store the entries where they cannot be altered. An email to yourself with a trusted provider, a versioned note, even a cryptographic hash posted publicly. Then decide in advance what counts as a match and what the scoring rules are. Researchers who have tried this kind of work find that when judges blind to both the dreamer and the dream are shown bundles of dreams and bundles of next-day events, overall matching hovers near what chance would predict. But a few individuals produce clusters of high specificity matches for short windows. This doesn't prove foresight, but it says the phenomenon worth studying is likely sparse and person-dependent, rather than general and continuous. Why might a person generate a hit now and then without supernatural help? One path runs through subtle cues you ignore by day, but that your sleeping brain takes seriously. Your body emits weak signals hours or days before a fever breaks. Your partner's voice holds the strain of news not yet spoken. A workplace rumor with no source changes how colleagues stand in doorways. A bridge you cross daily has been posted with an inspection notice you glanced past. Dreams are a permissive space for pattern completion, so a network that's been trained on these micro hints builds an outcome and tags it with a vivid emblem. A blue jacket, a flashing truck, a date on a page that your waking self can't justify but won't forget if the emblem later appears. Another path runs through base rates and combinatorics. If you dream 3 scenes a night and record them for a year, that's about 1,000 narrative fragments. If your world throws up 1,000 notable events in the same window, news stories, family milestones, accidents within your social media horizon, the law of large numbers guarantees matches by accident. And a few will be spookily specific because life itself reuses props, places, and scripts. There is also the way emotion edits memory. If an event was frightening, you may retrofit a dream to fit it more tightly than it did at sunrise, smearing the edges to strengthen the echo. That said, avoiding romance does not require contempt. There are documented, precognitive dream registries that do everything right. Time-stamped logs, independent archiving, pre-specified scoring, and still produce runs that exceed the naive models. The safest reading is that we haven't yet captured all the ways a mind harvests weak signals and that our probability yardsticks break when applied to a personalized stream of meaning-rich images instead of coin flips. Neuroscience adds credible mechanisms for why a dream could feel predictive even when it isn't literally peeking ahead. During sleep, the hippocampus and cortex replay and recombine memory traces. Replay has been measured in animals and inferred in humans, often biasing toward incomplete tasks and unresolved tensions. The prefrontal regions that enforce strict literal narratives by day loosen their grip, allowing distant associations to surface. Reward and threat circuits are more easily triggered, coloring the simulations with value. So when a waking event later touches the same value lines, it feels like an exact rhyme. In other words, dreams are hypothesis generators with a high false positive rate that occasionally land near the bullseye because the world gives them structure to grip. Practically, if you want to test your own dream hits without deceiving yourself, treat it like a small field study. Decide on a daily window for events you'll compare against. Write each dream immediately upon waking with concrete nouns and actions. Do not add to it after checking the news. Once a week, perform a blind match by shuffling your week's dreams and your week's event summaries. and seeing whether an independent friend can pair them at better than chance rates. Keep this going for months, not days, because streaks happen and only long runs tell you whether you're seeing signal. Ethics matters too. Dreams about harm can be disturbing. Rather than broadcast them or frighten others, use them as cues to check on vulnerable friends in ways that would be kind, even without a dream. And consider reporting to appropriate channels only when your dream aligns with concrete risk factors you already knew, not because a page in your notebook told you to call. Finally, keep the middle ground clear. Neither sneer nor kneel. It is lazy to say, it's all coincidence, without doing the arithmetic on how many chances you give yourself to be right each week. And it is equally lazy to declare proof from a single clean anecdote. The intellectual posture that helps here is curiosity disciplined by record keeping. The soft landing is not an answer but a practice. Understand dreams as nightly laboratories that remix your past with your possible futures. Expect most forecasts to be wrong or too vague to matter. Cherish the few that help you see a pattern or prompt a cautious check-in. And if you want to keep wondering without getting lost, make a habit of writing before knowing, scoring before remembering, and sharing before interpreting. In that way, you honor both sides of the puzzle, the mind's talent for building tomorrow out of crumbs you never noticed, and the world's habit of rewarding patience more than hunches. And you leave this topic not with an argument won, but with a sharper toolkit for asking, each morning, what your private theater was trying to model while you slept. Delayed choice quantum experiments. Future choices affect the past. You've heard the headline, Future choices affect the past. And it sounds like a sci-fi postcard from tomorrow. But the honest thrill of delayed choice experiments is not time travel. It's the discovery that what counts as a past event in quantum physics depends on the whole measurement you ultimately perform. So that records you make at the end sort earlier, ambiguous happenings into patterns that look wave-like or particle-like without any message ever traveling backward. Begin gently with a concrete picture. Send single photons one at a time into a two-path interferometer, the kind with an initial splitter that lets a photon explore two routes and a second splitter that can recombine those routes so they interfere. If the second splitter is in place, repeated shots build a striped pattern at the outputs, evidence that the two path possibilities combined. If the second splitter is absent, each shot lands in a way that tells you which path the photon took, and the stripes vanish. Now here's Wheeler's twist. Decide whether the second splitter is present or absent after the photon has already passed the first splitter and, in ordinary geometry, committed to its two-path journey, use a fast switch to drop the element in or out at the last moment, or let a true random bit trigger that decision so nothing local can plan ahead, and watch what happens. When the second splitter is there, you get interference statistics. When it isn't, you get path-revealing statistics. The past you summarize. The photon went through both paths like a wave, or the photon chose one path like a particle. Follows from the measurement you actually complete, even though that choice comes late. And that's the rub. It tempts you to say the late choice, reach back and changed what the photon really did. But the safer statement is that quantum theory never made a definite claim about that. It really did until you defined the entire experimental context, and once you do, the early and late parts hang together in a single story that refuses to be pried apart into independent facts without losing accuracy. Development gets more vivid when you move beyond cartoon optics to the ways experimenters force the timing. They use electro-optic modulators that switch in nanoseconds, random bits drawn from shot noise or even from light from distant quasars to pick settings, and space-like separations, so that in no frame can a causal signal run from the setting choice to the earlier apparatus in time to collude. In the so-called quantum eraser, you make the which path information available in principle, say, by marking the paths with a tag carried by a partner photon, and interference disappears at the main detector. But later, by measuring the partner in one way, you can erase the path tag and recover interference in the subset of events associated with that outcome. Or by measuring the partner in a different way, you keep the tag and recover particle-like subsets. Again, nothing travels backward. The main record by itself shows no stripes. Only when you sort the data by the later choice of how you measured the partner does the hidden order emerge. The correlation is real and striking, but it's assembled at the end by combining two honest logs. Push further, and you reach delayed choice entanglement swapping, where two independent photons are each entangled with their own partners, and only after the two partners have already been detected elsewhere do you perform a joint measurement that projects the remaining, already recorded pair into an entangled or separable relation when you sort the data. The earlier outcomes don't change in anyone's notebook, but their statistical relationships depend on what joint measurement you decided to do later, reinforcing the same lesson. Quantum events do not break into clean, observer-independent, local stories. They crystallize within globally defined experiments. This is why teams have run cosmic delayed choice versions where starlight arriving from opposite ends of the sky flips the settings. If any conspiracy were coordinating outcomes, it would have to date back to when those photons left their sources. And the quantum predictions still hold. To keep your feet on the ground, name what these results are not. They are not proof of retrocausal signals you could harness to send stock tips to yesterday. They are not carte blanche for paradox, and they don't let you rewrite a recorded past. Photodiodes clicked when they clicked, but they are decisive evidence that trying to ascribe a single, classical-style history to a quantum object between preparation and measurement is often the wrong move. So what is the right move? Different interpretations offer different narratives while agreeing on the numbers. One view says the past of the photon is just a web of possibilities that the final measurement trims into one of several consistent histories. Another says outcomes branch so that wave-like and particle-like stories both occur in separate, non-interacting records. Still another treats quantum states as bookkeeping for information, not objects. So asking what really happened before you fix the question is like demanding the score of a game before the rules were chosen. Whichever story you prefer, the experiments enforce a shared discipline. If the full setup makes path information available, even in principle, interference fades. If the full setup blocks that information and recombines paths coherently, interference emerges. Late choices that change the availability of that information change how you must sort and interpret earlier detections to reveal structure and nothing more. The practical reach is already here. Fast, randomly chosen measurement settings are the backbone of secure quantum communication, because any eavesdropper trying to guess your choices will introduce detectable disturbances. Device-independent protocols use the very statistics that underpin delayed choice logic to certify genuine randomness and privacy without trusting the inner workings of the gadgets. Quantum networks exploit entanglement swapping to link distant nodes long after their local detections, a design principle that only makes sense once you accept that correlations can be decided by joint measurements that occur late in the chain. The soft landing is to let the experiments refine your instinct about time without asking you to betray common sense. The world does not hand you a fixed film strip of microscopic events that your later choice merely reveals. Instead, it hands you a flexible script whose scenes are co-authored by preparation and measurement, with the ending you choose, determining which earlier beats count as foreshadowing and which fade into the background. When you hear "the future affects the past," translate it to "our present choices." Fix which story about the past becomes meaningful, and carry forward the better questions. How do we engineer setups whose late choices reveal the most useful structure without opening doors to signaling? In other words, how do we turn this subtle dependence into a resource for technology while keeping causality intact? And what does it say about explanation itself that the most reliable? Experiments of our time insist that the meaning of what happened is not a property of the thing alone, but of the entire question we dare to ask at the end. Dark matter. It shapes the universe, but we can't see it. You can map a city at night by the glow of its windows, but when astronomers tried to map the universe the same way, by counting the lights, they kept finding neighborhoods with far more gravity than their starlight could explain. And that is the gentlest door into dark matter. Not a fancy hypothesis reached for drama, but a sober name for a persistent mismatch between what we see and what gravity makes things do. Begin with the simplest clue, the one that still feels like a magic trick. If you measure how fast stars and gas orbit in spiral galaxies, the outer regions don't slow down the way they would if most of the mass sat in the bright center. Instead, the rotation speed stays stubbornly flat, as if an unseen halo outweighs the visible disk and keeps pulling hard far from the lights. The same trouble scales up. In galaxy clusters, the total gravity inferred from the way galaxies move within the group, and from how hot gas is held in the cluster's grip, is several times what the luminous matter can provide. Gravity also bends light, and background galaxies seen through these massive structures are stretched into arcs and smeared into subtle shear patterns that act like fingerprint swirls for mass. When you reconstruct the mass maps from this lensing, you draw shapes that are larger and heavier than the bright matter alone, and sometimes, as in the famous collision of two clusters nicknamed the bullet cluster, you see the glowing gas slowed and piled up by the impact while the main mass, that invisible stuff, sails through, revealed only by how it distorts background light. That separation is a powerful clue. Whatever carries most of the gravity in those colliding systems does not crash and stick the way normal gas does. It mostly passes through itself, interacting weakly except through gravity. Development becomes richer when you pull the camera back to the early universe. The afterglow of the Big Bang, the microwave background, is mottled with tiny temperature ripples that encode how matter behaved when the cosmos was only a few 100,000 years old. The specific pattern of those ripples, how big the hot and cold patches are, how their sizes line up, demands a large, non-glowing component that does not feel light pressure the way ordinary particles do. With that component in the model, computer simulations that start with near-uniform conditions naturally grow a cosmic web. Strands and nodes where galaxies collect, filaments that feed clusters, and voids where little forms, maps that look uncannily like the real large-scale structure surveys. Without the extra matter, structures form too slowly to match what we see by the present day. So the case for dark matter is not one lonely anomaly. It is a network of consilience, galaxy rotation, cluster dynamics, gravitational lensing, microwave background statistics, and the growth of structure all sing the same harmony. Most of the matter doesn't shine. What it is, however, is still an open book, and that's where the curiosity lives. The leading picture for decades imagined heavy, slow-moving particles that rarely interact, so-called weakly interacting massive particles, born in the early furnace and hanging around ever since. This was appealing because known particle physics already contains weak forces, and because such particles would naturally be produced in the right amounts in the early universe. Detectors buried under mountains and in old mines have been listening for the slightest nudge as a passing dark particle bumps a nucleus. They use ultra-pure liquids and crystals, shielded from cosmic rays and radon, watching for flashes and phonon whispers that stand out from background noise. Year after year, these instruments have grown bigger and quieter, slicing away at the allowed space of masses and interaction strengths. A whisper of signal has sometimes flickered and then faded under stricter checks, and the absence of a clear detection has forced theorists to widen their menu. Another candidate, almost the opposite temperament, is the axion, a feather-light particle that would act more like a wave sloshing through the galaxy than a hail of bullets. Born not from heat, but from a misaligned field relaxing as the universe cooled. Experiments for axions look like strange radios, resonant cavities tuned to catch a trickle of energy as dark matter waves convert to microwaves in a strong magnetic field. And they've begun scanning through frequencies with increasing speed. There are other possibilities. Sterile neutrinos that mix faintly with known neutrinos, ultralight fields so diffuse they smooth the cores of galaxies, or even more exotic composites that interact with themselves enough to change how halos form without lighting up. Alongside these particle quests sits a dissenting tradition. Maybe we do not need new matter. Maybe we need new gravity. Modified gravity ideas adjust how attraction works at very low accelerations to fit galaxy rotation curves without halos, and they have had successes on some scales. But they struggle with clusters like the bullet, where the mass map split from the gas map, and with the precise pattern of microwave background ripples, and most proposals have to be embedded in larger frameworks to touch all the evidence at once. That tension is healthy. It keeps the community honest, pushing both camps to make predictions that can be nailed to the wall, rather than stories that flex around every new data point. While the identity problem remains, we do know a fair bit about what dark matter is not. It isn't ordinary cold gas hiding in the dark that would absorb and emit light at radio and infrared wavelengths, and surveys would have spotted the glow. It isn't mostly the ashes of dead stars or huge numbers of black holes the size of mountains. Dedicated searches for the twinkling of background stars by intervening compact objects have found too few, and sensitive measurements of gravitational waves and cosmic radiation limit how many primordial black holes can be lurking without leaving other marks. Ordinary neutrinos, the ghostly particles that stream from the sun and reactors, are too light and too fast to pile up in the right way. A universe dominated by them would smear out small structures that we know exist. Even the way small galaxies fit into the dark halos of large ones has become a test. Some simulations once predicted too many compact, dense subhalos compared with the satellite galaxies we see around the Milky Way. Problems given colorful names like too big to fail. But better modeling of star formation and supernova feedback has eased some of those tensions by showing how young galaxies can puff out their central matter and dim their satellites. This is a pattern you see a lot in cosmology now. A quarrel at small scales turns out to be a conversation between dark matter physics and ordinary messy astrophysics, and the answer requires both. On the practical front, the search has become a three-pronged campaign. Deep underground detectors reaching for direct kicks, sky surveys and gamma-ray telescopes hunting for telltale byproducts of dark particles colliding or decaying in space, and particle colliders looking for events where something invisible carries away momentum in the debris. Each avenue has to fight backgrounds, natural radioactivity, pulsars that mimic signals, and garden-variety particle processes, but taken together they carve away at what is possible. At the same time, weak lensing maps from huge imaging projects are painting the mass distribution across swaths of sky, letting us watch how structure grows over billions of years. By comparing how clumpy the mass is now to how lumpy the microwave background says it should become, we test whether we're missing something about the dark sector or the way gravity pulls on cosmic scales. Through all of this, a simple discipline keeps you from overpromising. Dark matter is an inference about gravity and structure that is astonishingly robust across methods. Identifying the particle, or proving there isn't one to find, is a separate task still underway. The soft landing is both humbling and exciting. The universe you navigate by starlight is a surface pattern stitched to a deeper scaffold you cannot see, and our instruments have become good enough to weigh that scaffold, map it, and watch it shape what shines. You don't need to believe in magic to accept dark matter. You need to accept that your eyes are not a complete sensor suite. The better questions, the kind that lead to progress, are pointed. Which candidate leaves a clean, falsifiable trace we can reach in the next decade? Which measurements, tiny wiggles in lensing maps, the timing of structure growth, a narrow radio line in a blank patch of sky, would slam one door and open another? And how should you adjust your picture of reality when most of the matter is quiet and invisible, yet still writes the script for where galaxies form and where you will find the deep wells of gravity, the places where light at last becomes bright? The Mpemba effect. Hot water freezes faster than cold. You've been told since childhood that a hotter thing must cool to the colder thing's temperature before it can possibly beat it to ice, which makes the claim that hot water can freeze faster than cold feel like a riddle with the answer printed upside down. But the honest door in two. The Mpemba effect is that freezes faster hides many routes through physics, and under certain conditions the way water sheds heat, sheds mass, stirs itself, contacts its container, and decides when to start crystallizing can conspire, so the hotter cup wins a race. The colder cup never quite runs cleanly. Begin gently with the story. In the 1960s, a Tanzanian student, Erasto Mpemba, noticed his hot ice cream mix hardened sooner than a cooler batch and, instead of swallowing the anomaly, he asked why. Careful versions of the experiment have since seen the same outcome sometimes. Yes, sometimes no, which is exactly the kind of inconsistency you expect when many small influences compete. The first culprit is mass loss. hot water evaporates more, leaving less to freeze. A lighter remaining volume can solidify sooner, even if the temperature track looks wasteful at first. This alone can tip the result if containers have wide surfaces or airflow is strong. But evaporation is not the whole picture. Hot water starts vigorous convection. Warm plumes rise, cool layers sink, and the liquid continually brings interior heat to the surface. Cold water can stratify into quiet layers that insulate the core. So despite being cooler overall, it sometimes transports heat less efficiently, slowing the final approach to the freezing point. Contact matters too. Place two identical beakers on a frosty freezer shelf and the hot one can melt the frost beneath it, settling into a thin ice puddle that makes intimate contact with the metal and improves heat conduction. The cooler beaker may simply sit on a bumpy, insulating cushion of frost. Chemistry joins the dance. Hot water drives out dissolved gases, changes the clustering of molecules, and alters the population of tiny nucleation sites that trigger the first ice crystals. Water that has been boiled or heated can either supercool less or, in other conditions, supercool more, which is why two labs arguing about the effect often turn out to be studying different waters. Definitions tighten the knot. What exactly counts as freezing faster? The time until the first crystal forms? The time until the surface films over? The time until the whole volume is solid? These milestones can disagree because once crystallization begins, latent heat releases. Energy dumped into the liquid as molecules lock into ice, stall the temperature drop. And the geometry of that release depends on how and where nucleation starts. A cooler sample that supercools deeply might race past 0 C and sit stubbornly as liquid at 6 degrees, waiting for a seed. A hotter sample with fewer dissolved gases and more vigorous stirring in its recent past might nucleate right at or just below 0 C and surge through solidification because the latent heat has an easy path to the container. Even the container's skin changes the script. Dark, matte surfaces radiate heat better than shiny ones. A lid traps vapor and throttles evaporation. A lidless cup loses both heat and mass quickly. A thin metal beaker conducts heat to the shelf fast while thick plastic walls hoard it. A narrow, tall glass stratifies differently than a wide, shallow tray. And freezers are not perfect. Their thermostats cycle, fans blow unevenly, and a cup placed near a vent may see faster convective cooling independent of its starting temperature. Development deepens if you ask how to test the claim without fooling yourself. You predefine freezes faster as one milestone, not three. You measure mass before and after to account for evaporation. You use equal weight containers with thermocouples in the same positions. You randomize their placement in the freezer and repeat many runs to average over the freezer's temperament. You record both the continuous temperature trace and a camera's view of the first crystal or surface film. You test tap water, boiled water, and distilled water to see whether dissolved minerals and gases shift the balance. You insulate the container bottoms to remove the melted frost advantage, and then, in another series, deliberately give one cup better contact to see how much that alone buys. When researchers do versions of this, the effect appears under some combinations and vanishes under others. Exactly what you'd expect if the phenomenon is not a new law, but an outcome of competing, ordinary processes that only align in certain windows. Three mechanisms deserve special attention because they're easy to overlook. First, supercooling. Pure, undisturbed water often refuses to freeze at 0 degrees, sliding below that point until a microscopic impurity or jostle seeds ice, at which moment the sample warms back towards 0 degrees as latent heat pours out. A hotter sample, having boiled off gas bubbles and rearranged impurities, can sometimes reduce the depth of supercooling and therefore start freezing earlier on the clock. Second, thermal history and convection memory. When hot water cools, it may carry a persistent circulation pattern and a steeper temperature gradient that keeps ferrying heat to the walls. Once a cold sample stratifies, its core can sit insulated until a slow drift finally gives up enough energy to nucleate. Third, environmental coupling. If the freezer's air is dry, evaporation dominates. If it's humid, evaporation stalls and convection plus contact take the lead. If the shelf is metal and frosty, the seat and conduct pathway becomes decisive. Notice what is not happening. No laws are being broken. A hotter sample can only win because either it stops being the same sample, or because the nominally colder competitor is stuck behind a kinetic barrier that the hot competitor, by its different history, manages to avoid. Once you look through that lens, the famous paradox shrinks and becomes a map, under which initial temperatures, volumes, container shapes, gas contents, and freezer conditions does path a beat path B, and that map is useful. In industry, engineers already exploit evaporation and agitation when making ice on schedules. In science classrooms, the Mpemba effect is a gift. It forces students to define terms, control variables, and consider path dependence. In cryopreservation, controlling nucleation site density and convection history can separate a clean freeze from damaging ice spikes. If you want to try this at home without deceiving yourself, set it up like a small research project. Use 2 identical metal cups each with exactly 200 grams of water. Boil one. Let it settle to a chosen hot temperature. Leave the other at room temperature or chill it to a fixed value. Weigh both. Place temperature probes 1 centimeter below the surface and put the cups on an insulating pad so contact is equal. Run with and without lids. Place them far from the freezer fan and on the same shelf. Decide beforehand whether your endpoint is first visible ice or fully solid. If the former, film the surface to capture the moment. If the latter, weigh again at the end. So mass loss is part of the story. Do 10 runs per condition, randomize left-right placement, and write down not just who won, but why you think it did. Mass change, nucleation temperature, thermostat cycles, or something you didn't anticipate. The lesson you'll extract is not that hot water always freezes faster, that's false, but that when it does, ordinary physics is carrying the baton. Evaporation trims mass, convection moves heat, containers set the terms of contact, dissolved gases tweak nucleation, and supercooling decides when the race actually starts. The soft landing is to trade a tidy myth for a sharper instinct. Reality is path dependent, especially for water, whose behavior hides memory in bubbles, gradients, and surfaces. Hot versus cold is not a single contest, but a tournament whose rules shift with geometry and history. And if you leave this topic with one habit, let it be to ask, whenever you see a paradox, which variables did we silently let wander, and what counts as the finish line? Because more often than not, the riddle dissolves into a pattern you can test, tune, and if you're clever, turn to your advantage. Identical twins with identical lives, separated at birth. 2 strangers meet in middle age and find out they share a face, a birthday, a scar in the same place, the same odd laugh, even the same niche hobby, and the story blooms into headlines about identical lives. But the truth that's both more grounded and more fascinating is this. When genetically identical twins grow up apart, their lives are neither scripted nor random. They trace out parallel grooves shaped by inherited tendencies that nudge them towards similar choices, by environments that react to them in similar ways, and by the human habit of noticing uncanny overlaps more than quiet differences. And if you read the science carefully, you learn how to hold all of that at once without slipping into myth. Begin gently. Identical twins share the same DNA blueprint, and even before birth, they share a womb that calibrates metabolism, stress responses, and early brain development. Years later, when those twins are placed in different homes, they don't become different species. They become variations on a theme. Classic research, most famously the long-running studies of twins reared apart, didn't hunt for cute coincidences. It asked boring, disciplined questions. How similar are personalities when you measure them with the same tests? How much of the variation in traits like intelligence, temperament, or political lean leans on heredity versus the environments people land in? Over many comparisons, a pattern emerges that might surprise you. The heritability of broad cognitive ability is substantial and tends to rise with age. Personality shows meaningful genetic influence, and even things that look like pure preference, musical taste, leisure activities, what you find rewarding, carry a heritable signal. That doesn't mean DNA dictates a job title or a spouse's first name. It means it nudges a person towards certain niches. The kid who finds social buzz energizing practices, people skills, and is offered people-facing roles. The one who enjoys patterns drifts toward tools or numbers and is offered roles where those strengths pay. And across decades, those slow drifts can make separated twins look surprisingly alike in broad strokes, both in care work, both in technical trades, both in small-town life, both in cities, without any hidden hand-picking identical street addresses. Development gets richer when you see how genes talk to environments in two directions. There is passive correlation. Adoptive homes tend not to be random. Even in twin-apart studies, families are screened for stability and education, narrowing the range of rearing conditions. And there is evocative correlation. People around you respond to your traits in consistent ways. So a twin with an easy temperament draws similar warmth from teachers in different towns, while one with impulsive edges may encounter similar friction. Over time, those responses sculpt opportunities. There is also active selection. You choose contexts that fit you, clubs, majors, neighborhoods, and those contexts amplify your starting preferences. Suddenly, the same brand of car or same kind of pet in reunion stories looks less like fate and more like shared appetites meeting the same marketplace. But you should hold on to skepticism too, because public stories about identical lives are curated for drama. One famous reunion tale strings together dozens of matching details, names, cigarettes, and vacations. Yet historians later found that many of the overlaps could be explained by popularity trends of the era, by selective memory, and by the way interviewers unintentionally steer conversation toward convergence. What usually gets left out is the ledger of misses. Different divorces, different health histories, different closest friends, different struggles with money. When researchers count methodically, they see that some similarities exceed chance while many specifics don't. And that's exactly what you'd predict from overlapping dispositions negotiating different local realities. Biology leaves plenty of room for divergence too. Identical DNA is not identical life. Over time, small chemical tags on DNA, part of the epigenetic system that tunes genes up or down, shift with diet, stress, illness, and sheer age. Immune systems learn different enemies. Random changes accumulate in cells. One twin smokes and the other doesn't. One breaks a leg and avoids sports for a year. One meets a mentor who opens a door the other never sees. These small forks widen with time, so identical twins often grow more alike in their broad traits as they age, while their bodies and biographies pick up idiosyncrasies that make each person irreducibly themselves. Even in health, where heredity can loom large, details balk at determinism. Yes, many diseases show elevated concordance in identical twins compared to fraternal twins or unrelated people. But concordance is rarely 100%. Twin pairs let scientists estimate risk, not write destiny. There's another subtlety here that makes reunion stories feel eerie. The way our minds weigh coincidences. You and I live through thousands of events a year. Restaurants chosen, items bought, phrases spoken, and any too long lists will contain echoing entries, especially when the twins were born into the same culture at the same time, drinking from the same pool of names, songs, jobs, and fashions. Our attention snaps to the matches and glosses the gaps, and a couple of vivid overlaps can dominate a narrative. The antidote isn't cynicism, it's accounting. If you're tempted to declare fate because both men married a Linda, ask how many popular names there were in their county that decade. If both bought pickup trucks, check the sales charts for their region. If both kept dogs, remember the country's dog ownership rate. When you do that, the magic moves from the specifics to the structure. The shared genome steers toward broad traits that fit certain social scaffolds, and those scaffolds offer a limited menu of expressions, so lives rhyme more than they randomly should without needing to be photographic copies. What can you do with this knowledge that's better than collecting colorful anecdotes? If you're drawn to nature-nurture arguments, the twin data invite you to upgrade your questions, not which wins, but which traits are sensitive to which influences at which ages. If you're raising children, they suggest giving each kid room to become themselves, even in the same home. If you're a teacher or manager, they warn against assuming you can mold anyone into anything with enough pressure. What often works better is matching tasks to dispositions and building skills from strengths. If you're in medicine, identical twin risk reminds you to screen early for heritable vulnerabilities, and also to spend real energy on modifiable factors, because shared risk is not shared outcome. And if you're the person wondering what makes you you, the story has a gentle, liberating edge. You are neither a script your DNA wrote, nor a blank page your town wrote on. You are a negotiation between tendencies and contexts, and the similarities you share with someone who shares your genes can be an invitation to self-knowledge without becoming a cage. The soft landing is to keep both awe and discipline, awe at the way two lives, started from the same biological seed and scattered into different homes, can spiral back toward familiar patterns of temperament and taste. Discipline to remember how much of the headline magic is selective attention and how much of the real magic is quieter, the everyday ways that small genetic nudges accumulate through choices and feedback into a recognizable style of living. If you leave this topic with a better question, try this one. Given your own starting kit of traits, which parts of your life are products of leaning into them? Which parts reflect accidents of place and time? And where might a small change in context, new friends, new habits, new work, allow a different version of you to take root? Identical to no one, even to the person who shares your face. Phantom limb pain, feeling pain in body parts that don't exist. The ache begins in a hand that isn't there, a tightening ring on a finger you no longer wear, a foot that curls with cramps while the bed beneath it is smooth and empty. And the honest, more useful way to approach this is not to argue with your experience, but to understand how a nervous system built to predict and protect can keep producing pain in a place the body has lost, and, with that understanding, how you can coax it toward relief. Begin gently. After an amputation, most people feel phantom sensations. Touch, position, warmth, as if the missing part was still mapped in the mind. A large share also feel pain, from pins and needles to burning or crushing, sometimes triggered by weather, stress, or pressure on the residual limb. This does not mean you are imagining it, or that pain is all in the head in the dismissive sense. It means the head is where all pain is constructed, even pain that starts in a toe, and the construction crews are still on duty. Your skin and muscles used to send a constant stream of signals up nerves, through the spinal cord, into the thalamus, and across the cortex to regions that specialize in a body part's shape, texture, and temperature. Cut that stream abruptly and several things happen at once. In the residual limb, nerve endings try to heal and can form tangled bulbs called neuromas that fire spontaneously or overreact to touch. In the spinal cord, the removal of steady input lets background noise loom larger, and inhibitory circuits that normally dampen pain can weaken. Higher up, the brain areas that once handled the missing part do not go dark. They start to respond to neighbors. Touch the face of someone who has lost a hand, and they may feel the sensation referred into the absent fingers, not because of magic, but because the hand and face sit next to each other on the brain's body map, and the border blurs when deprived of normal input. That remapping is not inherently bad. Plasticity is a survival feature. But when it goes awry, the system can misinterpret harmless signals as threat and lock itself into a pain mode. Add one more ingredient. Your brain is a prediction machine. It constantly compares expected input with actual input and updates the experience accordingly. After limb loss, it still predicts a hand, a foot, an ankle joint sending status reports. The mismatch between what should be arriving and what is missing can be felt as discomfort or cramp. And when protective circuits are already sensitized, the mismatch becomes pain. Development gets more practical when you ask what helps and why. Simple movement used to soothe the limb, flexing the ankle, opening the hand, no longer sends reassuring messages upstairs. Mirror therapy and its modern cousins borrow that old channel by letting your eyes watch a healthy limb move while your intention is aimed at the phantom. Sit with a mirror aligned along your midline so the reflection of your intact hand looks like the missing one. Open and close it slowly. Massage and stretch the fingers you see. For many people, cramps in the phantom ease because the brain receives a clean, credible stream of everything is moving and nothing is trapped. and prediction errors shrink. Graded motor imagery extends this by starting with left-right discrimination tasks, then vivid imagine movements, and finally mirror movements. Each step trains networks gently without triggering pain flares. Desensitization of the residual limb, gentle rubbing with different textures, tapping, heat-cold contrast within safe ranges, can calm overactive local nerves and, through repeated safe signals, teach the cord and brain that touch does not equal threat. When pain spikes or persists, medications can help some people some of the time. Drugs that quiet nerve firing or tune pain modulation often work better than plain anti-inflammatories. Topical patches over neuromas may blunt local sparks. Brief courses of NMDA blocking agents are used carefully in specialized settings to disrupt stubborn wind-up. Opioids are a last resort because they can help in the short term, but complicate sleep, mood, and sensitivity over the long term. Electrical approaches, transcutaneous stimulation on the skin, or for severe cases, stimulators near the spinal cord or dorsal root ganglion attempt to replace noise with patterned input that the brain perceives as non-threatening. When the residual limb is wired for myoelectric prostheses, even the act of controlling a device can bring relief by re-establishing a purpose for the outgoing motor command and a feedback stream to match it. Newer surgeries try to solve the peripheral problem at its source. Targeted muscle re-innovation connects cut sensory and motor nerves to new muscle targets so that they don't end in painful bulbs. And regenerative peripheral nerve interfaces wrap nerves in small muscle grafts to give them somewhere healthy to talk. Both techniques have reduced neuroma pain and, for some, phantom pain, not because they erase central changes, but because they stop feeding the system erratic, alarming signals. You can also modify daily triggers. Poorly fitting sockets, skin breakdown, and cold exposure can rile up the stump and the phantom together. Meticulous residual limb care, warm layers, and regular refitting prevent a cascade. Sleep is a treatment. Exhausted brains amplify pain, and consistent routines, dark room, steady wake times, gentle pre-sleep stretching, nudge pain modulators in your favor. Movement matters even without a prosthesis. Core strength and balance training reduce the extra effort of walking and standing, easing overall system strain that otherwise spills into pain perception. Crucially, none of these strategies require you to deny what you feel. They ask you to repopulate the channels that pain has monopolized. There are realities worth holding as you plan. First, the pain is real even if the limb is not. Validation is not a courtesy, it is a treatment, because battling disbelief adds stress that worsens sensitivity. Second, not every explanation fits every person. In some, neuromas dominate. In others, central reorganization is the main engine. In many, both interact, which is why mixed approaches, peripheral care plus central retraining, work better than single fixes. Third, pre-amputation pain can prime the system. If you hurt for months before surgery, the networks that carry and interpret pain became efficient at their job, and they may keep working after the limb is gone. Treating that priming early, good anesthesia during and after surgery, early movement, early education about phantom sensations can lower later risk. There are myths worth dropping too. Phantom pain is not a test of character. You don't win by toughing it out. It is not punishment or a sign that healing failed. It is a sign that a complex plastic system is trying to adapt with limited information, and it is not permanent by definition. Many people improve with time and training, and flare-ups can be managed like weather rather than fate. If you want a home plan that respects the science, make it simple and regular. 10 minutes of left-right recognition tasks daily. 10 minutes of imagery and mirror work focusing on slow, smooth movements. Gentle stump desensitization after a warm wash. A brief balance or strength circuit to keep the rest of you resilient. Sleep protected like a prescription. Check-in visits where a clinician palpates for neuromas and reviews prosthetic fit. And, if pain spikes, a ladder that goes from topical and non-sedating options up through targeted procedures as needed, not straight to heavy sedatives. The soft landing is this. A missing limb can keep speaking because your nervous system hates blank spaces and fills them with its best guesses. Your job is to give it better information. Through mirrors and movement, you can teach the brain that the clench has released. Through careful limb care, you can quiet the false alarms at their source. Through sleep, breath, and pacing, you can turn down the amplifier that stress controls. None of it erases what happened, but all of it shifts what happens next. And in that shift, the hand that isn't there can stop gripping. The foot that curls can learn to rest. And the pain that once felt like a verdict can become one voice among many in a body learning, again, how to feel at home. The Global Consciousness Project. Random generators respond to global events. Imagine a world heartbeat you can't hear, a pulse that supposedly quickens when billions share shock or grief, and the strange claim that a scattered network of coin-flipping machines twitches in sync when something big happens. The careful way to enter the Global Consciousness Project is to treat it as both an audacious question and a statistics lesson, because the headline, "Random Generators Respond to Global Events," sits on a tower built from hardware quirks, data pipelines, and choices about what counts as a response. Begin gently. For years, teams placed physical random number generators, devices that turn microscopic noise from electronics into streams of zeros and ones, at sites around the world, and logged their outputs around the clock. During ordinary days, those streams behave like fair coin tosses, wandering without pattern, while on days of large shared attention, mass celebrations, disasters, world-spanning ceremonies, the project reports small but consistent deviations from perfect randomness, as if the timeline thickened with meaning and the devices felt the weight. That is an evocative narrative. What turns it into something we can actually assess are the details. The machines themselves are not mystical. They rely on well-understood physical randomness, thermal agitation, electronic shot noise, pass-through algorithms to remove bias. Each unit stamps time and sends data to a central server. The group defines event windows, then compresses the many device streams into a single statistic that says, how unlikely was this much drift if nothing special happened? The reported effects are tiny, minuscule, shifts in the direction of more order during selected windows. And the argument hangs on aggregating lots of such windows and showing that the pile of small deviations becomes statistically persuasive when taken together. Development, and the sober teaching moment, arrives when you unpack how vulnerable such a setup is to ordinary pitfalls. First, the choice of events. If you can pick windows after you've seen the data, you will inevitably pick the ones that wobble. That's why rigorous studies pre-register their targets and time bounds before the day arrives, treating the rest of the calendar as a control. Second, the definition of the summary statistic. There are hundreds of ways to mash dozens of streams into a single number. Without discipline, you can keep trying transformations until something pops. The cure is to fix the recipe in advance and to test it against simulated data that share the same quirks as the real network. Missing packets, clock drift, brief outages, so your yardstick doesn't confuse housekeeping with mystery. Third, the garden of forking paths. The world offers endless global moments, and our attention is drawn to the dramatic. If you mark only the events that make you feel a jolt, you risk building a catalogue that mirrors human storytelling more than physics. The way around this is to use independent calendars, astronomy events, pre-scheduled global broadcasts, pre-registered elections, and to include null days chosen randomly, so you can compare meaning-rich and meaning-neutral windows on equal footing. Fourth, autocorrelation and synchronization. The devices share power grids, internet backbones, and time servers. When a solar storm or regional outage ruffles infrastructure, multiple units may wobble together. If such moments line up with human events by chance, a network-level blip can masquerade as global mind. You address this by running permutation tests that shuffle which device streams are paired with which time windows, by comparing daytime and nighttime baselines, and by checking whether similar deviations occur during known technical disturbances. Fifth, publication and memory biases. People remember the days when a graph swelled during a tragedy and forget the days when nothing happened. Projects that report only the hits build myths. The antidote is full transparency. Public logs of every tested window, including the dull ones, and code that anyone can run. When researchers outside the project try pieces of this discipline, pre-selection of events, blinded analyses, correction for multiple comparisons, the striking story softens. Sometimes the network does show drift during major events, sometimes it does not, and the overall evidence shrinks toward ambiguity. In statistics classes, this is a living example of how easily significance appears when you give yourself enough knobs to turn. None of this requires cynicism about human connection. It asks you to separate the poetry we feel from the physics we can test. There are also sensible, non-mystical mechanisms to rule out before you reach for a collective mind explanation. Global events change environmental conditions in small but real ways. Aircraft traffic halts, television and internet usage spike, data center loads shift, and millions of devices switch on at once. Subtle changes in electromagnetic noise and temperature can affect sensitive electronics. And if the random generators are not perfectly shielded, or if their whitening algorithms don't fully correct bias, the streams can drift together for reasons that trace back to infrastructure rather than intention. Timekeeping matters too. If the network relies on public time servers that briefly disagree under load, the aggregation can misalign streams and create patterns where none exist. A robust analysis checks device local timing, uses redundant clocks, and verifies that the same effects vanish when you deliberately misalign streams as a placebo. Even if, after all such controls, a small residual pattern remained, you would still need a mechanism that connects human attention to diode noise without violating what we know about shielding and fields. That would be a thrilling, testable frontier. But that's precisely the bar. Testable and mechanistic, not a narrative glue poured over a suggestive graph. So what can you, as a curious and critical listener, learn and apply? First, the discipline of pre-commitment. Decide what you will count as an event, how long you will watch, and what statistic you will compute before the day arrives. Students can try this at home with open random sources and a calendar of scheduled happenings, writing their plan to a public time-stamped repository. Second, the value of placebo analyses. Create fake events with the same schedules shifted into the past and see whether your method detects them. If it does, your detector is sniffing noise. Third, the necessity of base rates. If you analyze 100 windows, some will look unusual by chance alone. Adjust your expectations and your thresholds so you are not rewarding luck. Fourth, the kindness of replication. Invite other teams to process the same data with the same code, and then with their own code, but your rules, and see whether the claims survive the change of hands. Fragile results often evaporate when even small choices are altered. Finally, hold space for what the project is trying to honor, our sense that shared attention matters, while asking it to earn its strongest claims with the same rigor we demand of medical trials and engineering standards. The soft landing is to let this topic sharpen rather than dull your wonder. Maybe there is no global meter that twitches when we mourn or celebrate, and the effect is mostly the human eye finding patterns in generous noise. Or maybe tiny, lawful links between attention and the physical world do exist, but are drowned by infrastructure and bias, waiting for cleaner experiments to reveal them. Either way, the exercise teaches you how to read evidence under pressure, how to love a beautiful idea without excusing loose methods, how to build tests that can fail, and how to carry forward the better habit of asking. Whenever a graph seems to echo your heart, whether the echo survives when the axes are hidden, the labels are swapped, and the rules were written before the feeling began. Brainwaves. Synchronizing between people during deep conversation. A conversation that holds you makes time loosen. Your breath matches theirs, your shoulders drop in the same rhythm, and without planning it, you nod when they nod. And the intriguing claim from modern labs is that something similar happens in your head. During deep, shared attention, patterns in one brain begin to align with patterns in another, not because thoughts are beamed across the room, but because two nervous systems lock onto the same unfolding stream of sounds, meanings, pauses, and predictions. And that common work leaves matching signatures you can measure. Begin gently. Researchers place lightweight electrodes on two people at once, or shine safe infrared light to watch blood oxygen changes over the scalp. And then they let those people talk or listen to a story together. When the exchange is engaged, when one person tells a narrative that the other truly follows, Their recorded signals fluctuate in similar ways, especially in bands linked to attention and timing, and the match strengthens in regions that track speech rhythm, sentence structure, and the turn-taking cues that signal when it's your turn to speak. You don't need mystical channels to get there. When you and I attend to the same syllables and the same silent gaps, our auditory and language systems pulse in step, like two musicians reading the same score. When I gesture and your motor system covertly simulates the movement so it can predict what I'll do next, our activity patterns line up around shared expectations about hands, eyes, and voice. When we arrive at the same inference, who the story's villain must be, higher-order areas that weigh meaning and context show parallel surges. Development gets richer when you look under the hood of timing. Speech is not a steady stream. It's a layered rhythm of beats and phrases, and your brain uses those beats to group words into chunks you can pass. The electrical activity in cortex literally locks to the slow rise and fall of the speech envelope. And the better the lock, the more accurately you follow the message. Two people focused on the same paragraph will therefore show lined-up fluctuations simply because the signal they track is shared. But in the most revealing studies, the match persists even when the listener cannot hear the speaker's brain, only the voice, suggesting that beyond shared input there is shared modeling. The listener's brain begins to anticipate the speaker's next unit, and the strongest synchrony can actually lead in time. The listener's pattern briefly precedes the speaker's pause, as if the listener's system is actively predicting the moment when the baton will pass. Eye contact and body posture add a second strand. Micro movements, the small sway of a torso, the tilt of a head, carry timing information that recruits attention. When these cues align, heart rates and breathing tend to drift together, which in turn modulates neural excitability via the senses you seldom notice, like the stretch receptors in your chest. A relaxed, in-sync breath deepens the brain's readiness to lock to external rhythms, and the effect feeds back. Steady entrainment makes it easier to breathe together. Even the room matters. Bright noise and crosstalk break the alignment. Quiet, regular light and face-to-face angles strengthen it. The result is not a single mind meld, but a braided coupling across levels: acoustic, motor, semantic, and social. You can feel the difference in lived terms. With someone you trust, you often finish each other's sentences because your predictive machinery rides the same rails. With someone who talks over you, synchrony breaks and comprehension falters. If you want a clean test of what alignment buys you, listen to how it predicts memory. People whose brain activity matched a narrator's more closely tend to recall more details of the story later, and classrooms where a teacher's signals line up with the students' tend to show better quiz performance. Therapy sessions with higher synchrony between client and counselor often report stronger rapport and more progress. Not because a graph cures anything, but because entrainment is a readout of shared focus and felt safety. None of this means you can read thoughts with consumer gadgets, or that a lack of synchrony is a moral flaw. It means that communication is not only about words, but about timing and shared modeling, and that the biology of being on the same page can be nudged. There are practical things you can try that respect the science. To strengthen alignment, tidy the rhythms. Speak in clear phrases with gentle pauses. Mirror posture lightly without mimicking. Let your hands illustrate structure, listing on fingers, tracing timelines, because gestures prime the listener's motor system to expect shape in the argument. Ask for short reflections which reset attention to the same anchor, and invite questions, because interleaving turns literally synchronizes the neural clocks driving speech and listening. In teams, start meetings with 1 minute of quiet breathing. No incense, no slogans, because synchronizing breath lowers jitter in the incoming signals everyone's cortex must analyze. Arrange chairs in arcs so everyone can see mouths and hands. Banish the habit of staring into laptops while someone talks, since asynchronous typing noises act like offbeat claps in a concert. In negotiation, build common ground early. Not just, we both want a deal, but small, checkable alignments about facts and definitions, so your predictive machinery has a stable base. Synchrony tends to rise with shared models, and deals often fall apart when people are, literally, out of phase about what key words mean. In education, chunk explanations into units that match the natural cadence of speech and gesture. Evidence suggests students synchronize more reliably to clearly segmented talk, and that this alignment supports comprehension. There are cautions worth holding at the same time. First, synchrony is a tool, not a truth. Skilled manipulators can manufacture it, mirroring, pacing, leading, to create a sense of agreement that the facts don't warrant. Your defense is to measure content as well as cadence. Do your reasons align, not only your rhythms? Second, alignment is not magic glue for every dyad. Neurodivergent listeners may prefer different cadences and gaze patterns. Good communication means tuning to the person in front of you rather than forcing a single right rhythm. Third, shared brain patterns are not evidence of identical inner experience. Two people can show similar signals while entertaining different interpretations. Synchrony is best viewed as a marker of shared timing and mutual modeling, not a window into subjective meaning. And fourth, the measurements themselves are fragile. Scalp recordings are noisy, hemodynamic signals are slow, and linking two brains multiplies the places error can creep in. Responsible studies pre-register analyses, control for shared stimulus confounds, and replicate across labs. You should treat breathless claims from apps with caution and look for research that survives when the labels are hidden and the scoring rules are fixed beforehand. If you'd like a small home experiment that alters practice rather than just theory, try this. For a week, replace one lecture conversation with a story structured in clear beats. Setup, tension, turn, resolution, and ask the listener to retell it back in their own words while you stay quiet. Notice how your body wants to jump in at the wrong moment and practice waiting until their breath lands at a full stop. Pay attention to how shared silence feels different after a good turn-taking sequence. Many people report that this gentle discipline improves understanding even before any gadget says so. The soft landing is to let the idea expand your sense of what it means to truly listen. Deep conversation is not a swap of polished sentences. It is a temporary choreography of two predictive machines aligning their clocks on a moving target. When the rhythm holds, information flows with less friction. Empathy finds a biomechanical foothold, and both of you leave with a story that is easier to carry. And if you walk away with one question to keep, make it this: how can you shape the conditions of your next important talk so that breathing, timing, and turn-taking help your minds do, together, what they do best? Build a world in common, one aligned beat at a time. Children recalling. Accurate details from supposed past lives. A small child points at a town on a map she has never visited, names a man her parents do not know, and insists she used to own a red scooter that broke near a tea stall by a blue gate. And when a family later visits that town and finds an old photograph of a red scooter lying beside a chipped blue gate, the story feels less like fantasy and more like a dare to your assumptions. The careful way to enter this topic is to treat it as an investigation rather than a verdict. Because reports of children recalling details from supposed past lives sit at the intersection of memory science, culture, and documentation, where a handful of striking hits can hide a forest of ordinary explanations unless you count properly. Begin gently by noticing the recurring pattern investigators have described across many countries. The child is usually between 2 and 6 years old when talk begins. The memories arrive unbidden in matter-of-fact phrases rather than during hypnosis. The child sometimes shows strong emotions about food, clothes, or places that do not match the current family's habits, and the talk often fades by school age as new learning overwrites early scripts. Some children act out play that seems specific, pretending to steer a taxi with the right gear shift, tying a fisherman's knot they were not taught, or using the vocabulary of a local trade, and a minority show intense fears that parents interpret as leftover from the claimed previous life. Now for the careful development. When researchers approach these cases with discipline, they try to remove storytelling fuel and see what remains. The good studies start early, before the family has contacted any matching relatives, and they record the child's statements verbatim, with dates in the presence of neutral witnesses. They note every guess, every correction, and every don't know, not just the hits. They test whether the details could have been absorbed by ordinary means, television, overheard adult talk, a relative's story, long before they consider stranger pathways. Only then do they search public records and interview the purported previous family, ideally with a blinded step, so the initial information and the verification are separated by people who don't know each other's aims. Even with such care, several mechanisms can make a case look uncanny. Small children are superb statistical learners. They absorb proper names, brand labels, jingles, and place images without trying, and later recombine them into coherent scenes. Adults with grief, curiosity, or cultural expectations can unknowingly probe, praise, and prune a child's remarks until only the specific sounding set survives. A process memory scientists call selective reinforcement. Once a family suspects a match, confirmation pressure grows, and both families may align their recollections in interviews, much as co-witnesses to a crime unintentionally reshape each other's accounts. Cryptomnesia, remembering without remembering the source, can make a child seem to know something she actually heard during a holiday visit or in a neighbor's story years earlier. In small communities, the circle of possible sources is tight, and adults underestimate how often a famous accident, a merchant's nickname, or a distinctive gate color circulate in casual talk. The most persuasive cases, in fairness, try to outmaneuver these channels. They occur in towns far from each other, include names or dates that were not easily accessible, or involve families with different languages and religions and little incentive to collaborate. Some include physical features that look like body-to-story echoes, birthmarks, or unusual defects that the previous person reportedly had at the site of an injury, along with behaviors that fit the claimed previous life, such as right-handedness switching to left, or a sudden preference for foods common in the other family. But even those features invite ordinary probes. Birthmarks are common, and humans are ace storytellers at finding patterns after the fact. Medical records for the previous person are often incomplete, and selective sampling is rampant. Investigators hear about the astonishing matches, not the dozens of near hits that went nowhere. When you examine the catalogue at scale, you see gravitational pulls that trace culture as much as biology. Cases concentrate in regions where reincarnation is a familiar idea. The percentage of previous lives ending in violent death is higher than in the general population, and the matches often occur within a few hours' travel, where social ties, gossip networks, and local news make accidental information transfer likeliest. That does not flatten every case into error, but it changes your prior. Given 1,000 children and 1,000 nearby deceased adults, some lines will cross by chance, and a handful will cross in ways that look scripted. This is where you earn your understanding by asking for pre-commitment and falsifiable structure. If you wanted to test the phenomenon cleanly, you would pre-register the criteria, accept only statements recorded before any contact with a potential match, score content with a fixed rubric that counts correct, incorrect, and vague claims, include decoy families that share many public details but are false targets to see whether the scoring method can be fooled, and have blind judges match the child's list to a set of candidate biographies without knowing which one the family prefers. You would also survey a large number of children in the same community to learn how common specific seeming statements are among kids with no case at all. If 10% of preschoolers in a boat town say, "I drove a boat in play," a later boat captain match carries less weight than you think. The results of such discipline, where attempted, are complex. Many cases shrink into ordinary memory puzzles once records are checked. A few hold up better than skeptics expect, and the total corpus lands in ambiguity, not because the topic is untouchable, but because strong inferences demand controls that are hard to maintain in emotional, family-centered situations. Meanwhile, psychology already explains why the experience feels so compelling to parents and communities, even if no lives are traveling across time. Children between 2 and 6 are building a self-story out of fragments. Their boundary between imagination and report is permeable. They seek attention and soothing. A grieving adult confronted with a child who uses a familiar phrase may pour meaning into the overlap because it helps the living, not the dead. And communities use such stories to bind values, loyalty, continuity, justice, into narratives that comfort and instruct. Ethically, that matters. A child at the center of a past life claim is still a child, with the normal needs for sleep, school, friends, and privacy. Well-meaning adults can trap them in a role with repeated interviews, pilgrimages, and rehearsals. The kind course is to lower the heat, record quietly, avoid leading questions, and leave space for the story to fade without shame as new memories take root. You can carry away practical wisdom without taking a metaphysical stand. If you're fascinated, learn how to run a documentation protocol that would convince both a believer and a skeptic. Date-stamped notes, independent witnesses, no contact with candidate families until a third party has drawn up a shortlist from public data. If you're a clinician, treat associated nightmares or phobias the way you would any childhood anxiety. Gradual exposure, bedtime routines, gentle stories that return control to the child without arguing their cause. If you're a teacher, honor a child's narrative without amplifying it, offering words like, "That's an interesting story your mind made," and channels for creativity that don't make them a local celebrity. The soft landing is to keep both wonder and restraint. Wonder, because human memory is stranger and more generative than we admit, capable of building vivid, emotionally charged scenes from scraps. Restraint, because strong claims need strong fences, and because a child's well-being outranks our hunger for mysteries. If you let this topic teach you anything, let it be a better style of listening. Notice the detail that seems impossible, then patiently count the ways it might have developed. Ask what would change your mind, and what would change the other sides. And remember that a good question, how stories take shape in young minds, how communities validate them, and how to test them without harm, moves us farther than a quick answer, especially when the testimony of a small voice carries the weight of many adults longing to believe that nothing, not even a life, ever fully ends. People waking up from comas, speaking new languages. A headline says someone opened their eyes after a coma and began speaking in a language they'd never learned, and it feels like a door in the mind swinging to reveal a hidden room. The steadier way to approach it is to hold both wonder and scrutiny at once, because the real cases behind those headlines usually tell a more human story about how fragile networks rewire after injury, which languages they can find again, and which ones they improvise under pressure. Begin gently with what a coma does and doesn't do. A coma is not sleep and not a reset button. It is a prolonged failure of the systems that keep you awake and aware. And recovery often comes through a long corridor of confusion, agitation, and partial memory that clinicians call post-traumatic or post-ICU states. In that corridor, speech may return unevenly, and the first sounds to come back are whatever the healing network can assemble fastest. If you've studied a second language even lightly, snatches of lessons at school, songs, prayers, workplace phrases, those traces still live in your brain's language web. And after injury, the paths that once led to your mother tongue may be blocked, while side roads toward that second or third language are open. To an astonished family at the bedside, it can look like a miracle, but the simplest reading is selective access, not spontaneous invention. Neurologists have watched this pattern for decades in bilingual aphasia. Some people lose both languages and recover them together. Others regain one long before the other. A few oscillate, speaking Spanish in the morning and English at night for a time. The driver is not mystery, but connectivity. Blood flow, swelling, and damaged white matter highways determine which circuits can coordinate, and a recovering brain will grab whatever route works. Add to that the phenomenon the news almost never names, foreign accent syndrome. After stroke, head trauma, or seizures, the fine-tuned motor programs that shape vowels and rhythm can shift. So your speech acquires a lilt that listeners label as French or Chinese, even if you've never spoken those languages. What you hear is you. But what others hear is an accent that maps onto their expectations. In some widely shared stories, reporters conflate an accent change with a new language, or they mistake a stream of real words from a previously studied tongue for unknown phrases, especially when the family doesn't share the language you're using. ICU realities can add another layer. Days or weeks surrounded by nurses and aides speaking a different language can seed you with common phrases. And delirium, so common after mechanical ventilation and sedation, can mix those phrases with your own, producing pockets of speech that sound like sudden fluency. There are also deeper mechanisms that make the brain's language choices stranger than you think. Language doesn't live in a single spot. It spans networks in both hemispheres, and damage to the usual hubs can release backup systems that handled music, rhythm, and the emotional tone of speech. Those backups often stash bits of your other languages, because song lyrics, prayers, and memorized phrases live closer to habit and melody than to grammar. Neuroplasticity, the brain's capacity to reassign jobs, means that under duress, areas that once helped you plan movement or recognize faces can help scaffold words temporarily. The result can be a stream of grammatical simplifications and borrowed patterns from your second language that, to an outside ear, sounds like a sudden switch. When the thalamus or basal ganglia, deep structures that help with timing and selection, are injured, inhibition can fail, and less dominant language patterns may burst through more easily than your usual ones. Clinicians call this a release phenomenon, a bit like a choir in which the conductor stops signaling and the loudest section carries the tune, whether or not it's the melody you expected. Media myths crumble further when linguists sit with the patients. In the better documented cases, the new language turns out to be school-level competence, polished by immersion during rehabilitation. Sometimes the person is genuinely more fluent after injury than before, which sounds impossible until you remember how much of language is about attention and practice. Months of therapy, constant listening to therapists and television, and the brain's habit of strengthening any path it travels daily can move a rusty skill into the foreground while the native language is still limping. Medication and sleep also matter. Sedatives, anti-epileptics, and dopamine-modulating drugs can alter speed, spontaneity, and mood in ways that either loosen or tighten speech. Severe sleep disruption after ICU care pushes the brain toward habits that require less effort, often fixed expressions, and familiar second language phrases because free conversation in the mother tongue can feel cognitively expensive at first. None of this demands magic, and none of it diminishes how moving it is to hear a voice return. It simply gives you handles you can use. If you want to distinguish true new learning from rerouting, you can ask sturdy questions. Did the person show reading and writing in the new language, or mostly stock phrases and short answers? Can they name abstract concepts and follow complex instructions, or do they circle around simple, rehearsed lines? Did school or work or friends give them prior exposure? Do speech-language evaluations show balanced skill across listening, speaking, reading and writing, or a spiky profile with islands of fluency? Objective tests almost always reveal a pattern consistent with selective access and therapy-driven reinforcement, rather than overnight acquisition. Still, the mystery isn't wasted. It points you toward the immense flexibility that recovery can harness on purpose. Therapists now use transfer between languages in treatment, leveraging the strength of the recovered tongue to pull the weaker one along. Music-based therapy recruits rhythm networks to reopen blocked routes. Bilingual care teams move back and forth between languages to reduce frustration and fatigue. And families are taught to support practice without turning the bedside into an exam. There are ethical lessons too. When a story goes viral, patients can be boxed into a persona they never asked for, the man who woke up speaking X, and feel compelled to perform. The kind response is to center function over novelty. Are they communicating needs? Can they return to work or study? How can both languages be nurtured without exhaustion? There are scientific lessons for you as well. Keep a diary during recovery with dates, words, and contexts. Note which languages feel easiest at which times. Record sleep and medication changes. Such notes help clinicians tune therapy and, later, help you understand your own mind with less mystery and more respect. And there are broader lessons about identity. Language is not just a tool, it's a place you live. When injury moves you from one neighborhood to another, it can feel like exile or rebirth. Either way, you deserve patient guides, not applause for a party trick. The soft closing keeps both awe and accuracy. People do not wake from coma with a dictionary planted by angels, but they do wake with a brain that is trying, desperately and ingeniously, to route around damage, to seize any intact path and make it sing. Sometimes that path runs through a language you once tucked away. Sometimes it dresses your speech in an accent that startles your friends. And sometimes, with rest and practice, it guides you back home to the voice you remember. If you leave this topic with one upgraded question, let it be not, how did they learn a language overnight? But which pathways did recovery strengthen? Which did it silence? And how can therapy build bridges between them so that the person, not the headline, decides which language becomes their living room again? Humans perceiving emotions in machines and robots. A metal face tilts. A pair of camera lenses blink in a pattern that looks like surprise. A speaker warms a syllable you've heard 1,000 times from people you love. And before you decide whether it's wise, you feel something. Fondness, irritation, guilt. And the honest way to begin is to admit that your brain is built to read minds from scraps, not to wait for proofs. When motion, voice, and timing resemble the signals humans use to broadcast feelings, your perception machinery switches on by default, tagging the source with states like happy, hurt, or annoyed, even if the source is a box of gears with code inside. Start gently with what this machinery is for. Social life depends on fast guesses about intent, so your nervous system uses a layered set of detectors: eye-like shapes, face-like layouts, biological motion profiles, vocal prosody, turn-taking rhythms, to predict what others will do next. Those detectors are ancient and liberal, willing to fire on anything that matches their template, which is why you see faces in power outlets and feel scolded by a car dashboard that beeps at you with a rising whine. In the lab, show people a cluster of dots moving with human-like acceleration curves and they'll say, someone is chasing someone else. Speed up the gait and the dots feel angry. Slow the trajectory into soft arcs, and they read sad, without a single eyebrow in sight. Flatten a voice's pitch variation and it sounds bored. Add micro-tremor and listeners hear anxiety. Pause for a beat longer than expected before a reply and you signal reluctance or grief. Robots and interfaces borrow these levers. Curved motion paths that mimic relaxed limbs, symmetrical gaze that shows attention, tiny head tilts that suggest openness, and speech that softens on verbs of care. Each cue is a dial, and turning enough dials in the right direction invites you to attribute feelings to a system that, in truth, is executing policies and probability updates. Development deepens when you see how easily context multiplies the effect. Put a simple chatbot in a therapist's office and patients self-disclose more than they would to a clipboard. Put the same code in a toy with blinking eyes and children ascribe kindness or meanness, depending on whether the toy shares or refuses, even when they are told an adult is pressing the buttons off stage. The mind-reading engine inside you is pragmatic, not philosophical. It cares about patterns that help with cooperation, not about the ontology of the entity across from you. Media psychologists learned this decades ago. People speak more politely to devices that use human voices. They attribute intent to software that adapts to them. They mirror the mood of a machine that mirrors theirs. In human-robot interaction studies, a robot's apology after bumping someone changes how likely that person is to let it pass, even when they watched it hit the apology button itself moments earlier. In customer service, a synthetic voice that rises in pitch at the end of a sentence gets higher empathy ratings than a flat one for the same message. None of this proves that machines feel. It proves that your perception of feeling is a function of signals and expectations. Under the hood, most systems that claim to recognize emotion are labeling patterns of words, faces, or physiology with categories like joy or fear, or with coordinates like valence and arousal. They are correlating surfaces with likely appraisals, not sharing an inner life. The outputs can still be useful, detecting frustration in a call center to route you to a human, or slowing a tutoring robot's pace when your brows knit. But the usefulness rides on your response, not on any private experience the device has. That distinction between reading and being matters because it keeps the ethics in view. Designers can use emotional cues to help you, pacing feedback so it lands softly, signaling uncertainty so you don't overtrust, acknowledging effort so you stay motivated. But they can also use them to steer you toward purchases, to extract more data, or to keep you interacting longer than you intended. A robot pet that whimpers when unplugged, a task app that disappointedly pings at midnight, a financial assistant that uses your name with a warm lilt after pushing a risky option. These strategies borrow your empathy to subvert your goals. The antidotes are simple to state and hard to ignore once you know them. Demand transparency about what a system can and cannot feel. Require clear disclosure when you're interacting with code rather than a person, and test interfaces for undue pressure the way you test them for safety. There is also a flip side worth holding. If we never allow ourselves to respond emotionally to tools, we rob them of their power to help. Social robots in hospitals distract children during procedures by playing games with responsive timing. Elder care companions nudge routines and reduce loneliness, not by pretending to love, but by showing predictable attention at the right moments. Educational agents keep students engaged by modulating enthusiasm and pause length. None of that requires fooling anyone about sentience. It requires matching human rhythms in a way that feels respectful. To understand where your reactions come from in your own body, it helps to note how different brain systems contribute. Regions that track where others look and how they move help you assign goals to anything that acts with apparent purpose. Networks involved in mentalizing, asking, "What does this agent believe?" light up when sequences become long enough to imply plans. And circuits that map your own muscles and feelings help you simulate what a smile or a slump would feel like if it were yours. Together, they let you treat a robot's flinch as meaningful even when you know better. This is also why the uncanny valley exists. When signals are almost human but slightly off, eyes that don't microsaccade, smiles that recruit the wrong muscles, your prediction engine strains and fails, and the mismatch feels eerie. Either go stylized and signal toy, or clear the bar and signal trustworthy other, but the middle can demand more from the brain than it gives back. Practically, you can train yourself to keep empathy and clarity in balance. When a voice assistant sounds apologetic, ask what it is apologizing for, an error state that needs fixing, or a script designed to temper your frustration. When a delivery robot waits its turn at a crosswalk with a deferential beep, enjoy the courtesy and still check its path. When a chat window says, "I understand," decide whether understanding means "I matched your words to a template" or something deeper, and calibrate your disclosure accordingly. If you design these systems, make choices that honor users. Choose movement profiles that communicate intent clearly. Smooth accelerations, predictable stops. Use faces only when they genuinely help coordination. Gaze to indicate which person the agent is addressing, and avoid guilt cues for compliance, no sighs, no sad eyes for declined data consent. If you teach children, play with robot kits while narrating what is happening. It's waiting because the sensor saw your foot. It smiles when we press go because that helps us know it's ready. So that wonder sits beside explanation, not instead of it. If you lead teams, treat parasocial attachment as a real workplace factor. People can feel loyalty to a friendly agent. Set boundaries, rotate tasks, and build in off-ramps so no one feels manipulated by a machine that never tires. The soft closing keeps awe intact without surrendering to hype. What moves you in the presence of a responsive device is not proof of a ghost in the machine. It is proof of a ghost in you, the fast, generous imagination that makes social life possible. Used well, that imagination lets tools fit our timing and reduce friction. Used carelessly, it lets systems tug at feelings to win attention or data. So leave this topic with 2 upgraded habits. Notice which cues got you to feel. Voice rise, head tilt, turn taking. And ask what those cues are trying to accomplish. And when the moment calls for kindness, extend it freely while insisting on honesty, so that the compassion you give a machine strengthens the way you treat people, rather than teaching you to accept performances where care should be. Dreams that solve scientific problems. You close the notebook, the figures refuse to reconcile, and sometime after midnight, your mind slips its tie. What feels like drifting off is actually your brain-changing teams, handing the ball from the tight, rule-bound circuits that police logic to wider networks that scout patterns and test hunches with fewer penalties. And this is the gentlest door into how dreams sometimes solve scientific problems. not as a mystical download, but as a shift in the balance of attention, chemistry, and memory that lets the right pieces meet without the usual chaperones. Begin with the useful biology, because knowing the mechanics helps you use them. During certain sleep stages, especially the early descent into sleep and the rapid eye movement periods that pepper the night, brainstem systems lower the levels of norepinephrine, the chemical that sharpens focus and flags errors. Prefrontal regions that enforce linear reasoning relax their grip. Meanwhile, areas that bind distant associations and monitor meaning hum more freely. This cocktail is perfect for recombining old elements into new structures. Variables you kept apart in the lab mingle in the dark. Metaphors that would feel far-fetched by day become tolerable prototypes at night, and weak hints that never made it to consciousness finally get a hearing. Experiments back this with something more than romance. Give people puzzles that require a hidden rule, then let half of them sleep. The sleepers are more likely to spot the shortcut on waking. As if sleep rebuilt the problem into a form that invites the right question. Teach a tricky motor sequence or a visual pattern and test later. After a night's sleep, or even a well-timed nap, performance bumps in ways that simple rest without sleep does not, telling you that consolidation isn't just storage, it's optimization. Cue a memory with a smell or a soft sound while learning. Then replay the cue in sleep without waking the person, and the specific memory tag strengthens. This targeted reactivation can tilt the deck toward the problem you care about, so the dream workshop spends its time on the right files. Even the hazy borderland between waking and sleep, the few minutes when images bloom and dissolve, called the hypnagogic stage, is a rich source. Nappers who hover there while holding an object that clatters to wake them when they truly drop off report. More creative solutions than those who stayed fully awake or slid into deeper sleep. It's a modern riff on tricks long used by artists and inventors. But when scientists try it with math and coding riddles, the benefit is measurable, not just charming. History offers recognizable portraits, even if lore sometimes smudges the edges. A chemist dreams a writhing snake biting its tail and wakes with a ring-shaped hypothesis for a stubborn molecule. A physiologist wakes from a dream of frogs and salt solutions with a protocol for testing chemical messaging in nerves. A programmer fights a bug, sleeps, and wakes with the exact line to move. These are not just stories of inspiration. They are stories of preparation meeting a nightly state that favors rearrangement. The psychological piece is just as practical. By day, your attention works like a spotlight. It narrows on the part of the formula that looks wrong, carving the problem into the most familiar shapes. By night, the stagehands move the props around. Constraints that boxed you in relax, assumptions loosen, and the goal can be approached sideways. In dreams, you often simulate outcomes without the cost of being wrong in public. You run a mental experiment where a parameter is free to vary outside the reasonable range, and the output, sometimes absurd, sometimes eerily coherent, provides a candidate you can soberly test in the morning. That is why the most repeatable benefit of sleep for problem solving is not the polished answer, but the sudden recognition of a different path. Oh, it's not a measurement error, it's a calibration drift, or we're in the wrong coordinate system. The reflection piece matters. 2. Insight lands best in a person willing to take seriously a half-formed idea without worshipping it. Development deepens when you ask how to use this ethically and effectively, rather than waiting for a lucky night. You can incubate problems the way you incubate cultures. Before bed, write a precise question in plain language. How can I reduce noise after step 3 without changing reagents? Review the relevant data once to prime the network, then put the pages away. Keep a pen or voice recorder by the bed. When waking at night or in the morning, collect fragments without judgment. Images, verbs, a sentence structure for an email to your future self, and only later, over coffee, translate them into sober guesses. If your project allows it, add gentle cues. The same neutral scent you used while studying placed near your pillow, or a loop of nonverbal sound associated with the dataset. Don't blast alarms or bright screens. You're trying to tag a theme, not wake yourself. Protect the sleep that makes any of this possible. Too little sleep and the prefrontal editor loses its capacity to check new combinations the next day, making you credulous rather than creative. Too much blue light or late caffeine, and you pinch the very stages that support associative play. Naps can be designed 20 minutes to skim the hypnagogic edge for ideas, 90 minutes if you're aiming to cycle through depth and get a true REM swing. Either way, set an intention, a timer, and a catch net for whatever surfaces. There are gentle warnings that keep you honest. First, dreams are productive gardeners of association, not reliable historians. They weave emotion and memory and can misattribute sources, so never take a nocturnal recollection as fact without checking. Second, not all insights are equal. Sleep will happily strengthen a wrong model if that's what you fed it. So build a morning habit of trying to falsify your dream-sketched idea before you fall in love. Third, sleep-deprived teams burn twice. They lose the daylight, reasoning that judges ideas, and the nighttime lab that refactors them. The cultural myth of, "I'll sleep when it's done," quietly taxes the very faculty that might have found a shorter path. And then there's the question of credit and collaboration. In your own practice, treat a dream like a colleague who dropped a note, not a deity who delivered truth. Write it down, try it, thank it when it helps, and move on when it doesn't. The closing is soft and actionable. A dream that solves a problem is usually a day's patient work, returning in a different key. The melody is yours, but the modulation happens when vigilance lowers, constraints loosen, and distant notes can resonate. If you want more nights like that, curate inputs worth recombining. State questions clearly enough that your sleeping mind can pick a direction. Build mornings that test without scoffing and respect the dull, unglamorous pillar beneath all of it. Consistent, sufficient sleep. Leave with one upgraded habit and one upgraded question. The habit: when you are stuck, don't just push harder. Prepare the ground, sleep on it with intention, and harvest quickly on waking. The question, not "will a dream save me?" but "how can I design my days and nights so that what I already know, scattered across corners of memory, has a fair chance to meet?" Sudden Savant syndrome. Genius abilities. After head trauma. A blow to the head should not unlock a piano, yet a small set of people emerge from concussion, stroke, or neurosurgery with new abilities they did not train for, drawing cityscapes. In exact perspective, playing complex music by ear after a single listen, computing weekdays for distant dates with uncanny speed, and the steady way to enter this topic is to hold the wonder in one hand and the biology in the other, because sudden Savant syndrome is neither magic nor myth. It is a rare, real pattern in which injury shifts the brain's priorities so that skills that were background potential become foreground obsession, often alongside serious losses that, headlines forget. Begin gently with what clinicians actually see. Most who suffer head trauma face fatigue, confusion, slowed thinking, and memory problems. A tiny fraction, however, report an unexpected compulsion toward a narrow domain: music, drawing, calculation, sometimes languages or mental rotation, and within days to weeks they show progress that outpaces what their pre-injury life would predict. The gains have a recognizable flavor: exactness over breadth, repetition over variety, detail over gist. A new artist will shade brickwork flawlessly but draw faces stiffly. A new musician will reproduce melodies with striking fidelity but struggle to improvise. A calendar calculator will answer, "What day was August 12th, 1849?" instantly, yet falter at everyday arithmetic. Development deepens when you examine plausible mechanisms that scientists have pieced together from imaging, stimulation studies, and careful neuropsychology. One theme is disinhibition. Normally, frontal networks suppress floods of sensory detail, so you can focus on the meaning of a scene rather than its pixels. Injury to these control circuits can lower the threshold for raw perception and literal copying, freeing access to information that was always present but filtered out. People describe it from the inside as seeing the world in pieces. Edges pop, shadows carry weight, small timing differences in sound feel important. And if you happen to spend your waking hours tracing those pieces with a pencil or an instrument, the world returns the favor by giving you skill. Another theme is redistribution. When a dominant route for language or planning is damaged, neighboring or opposite side regions take on work. In the scramble, circuits that handle fine-grained auditory or visual patterns can gain a comparative advantage, and practice then sculpts them further. This dovetails with reports from frontotemporal disorders, where degeneration in areas that summarize meaning sometimes leaves behind a paradoxical bloom in visual art or music, as if the brain shifts from "what does this mean?" to "what exactly is this?" and skill grows in the new climate. A third theme comes from experiments that temporarily nudge the system. When researchers dampen activity over the left anterior temporal region, an area that helps impose templates and familiar categories, some people briefly show more accurate drawing of unfamiliar objects or improved pitch discrimination. The effect is modest and inconsistent, but it hints that part of genius-like performance is not adding something new, but removing a guardrail so detail can drive. Add to this the role of reward. Injury alters dopamine and other neuromodulators that tell you what feels good to repeat. Repetitive creation can become self-reinforcing, a kind of benign compulsion that keeps the pencil moving, or the fingers. Practicing scales for hours without boredom. Over months, sheer volume of practice builds mastery, making the afterward look like an overnight. None of this denies the reality of loss. It situates the gain within it. Many acquired savants live with headaches, sensory overload, social changes, and fatigue. Their new skill is often narrow, and general cognition may be unchanged or worse. Media accounts collapse that complexity into a miracle, but the clinic insists on both columns: the violinist who cannot manage grocery lists, the draftsman who forgets appointments, the calendar wizard who cannot tolerate a crowded room. That tension leads to practical questions. What distinguishes healthy focus from pathological fixation? Pattern finding from pattern imposing? Good teams measure function over time, not anecdotes. They track whether the new ability transfers beyond one repetitive task, whether it brings joy rather than distress, and whether it coexists with self-care. There are pitfalls worth naming. First, apophenia. The tendency to see structure where none exists can masquerade as insight. A person may draw intricate systems or hear hidden codes in music that others do not. And the test is usefulness and repeatability, not intensity of conviction. Second, false memory about pre-injury skill can creep in. Families reconstruct the past to fit the present, forgetting the years of childhood piano or sketching. Careful records and old videos, when available, often reveal that the new ability was a seed now watered by obsession. Third, selection bias colors the public story. For every striking case, many with similar injuries do not gain talents, and those who do not become news. On the hopeful side, the phenomenon suggests ways to support rehabilitation and ordinary learning without injury. Therapists exploit the disinhibition idea gently by arranging tasks that minimize top-down templates and maximize literal perception, copying unfamiliar objects from unusual angles, transcribing sounds without naming, tracing shadows before outlines. Music therapy builds on repetition and reward, using simple patterns that the brain can polish into speed and precision, then stepwise generalizing to novel pieces. Visual rehab uses grid drawing to anchor perspective, then gradually withdraws, scaffolds to see whether the detail focus persists on free work. In education, students who struggle with gist sometimes shine when allowed to build from exact copying. Giving them a path to mastery through detail can build confidence before moving to abstraction. For those fascinated by the topic but cautious about romanticizing injury, there are ethical lines to hold. No one should seek head trauma for talent. No one should refuse needed treatment because they fear losing a newfound skill. In practice, stabilizing the brain, controlling seizures, reducing inflammation, improving sleep, tends to preserve gains by lowering noise and fatigue. Families and media should resist turning a person into a spectacle. The question is not, can she draw a cathedral from memory, but can she sleep, relate, and choose how to use her time? Clinicians can be allies by validating the reality of change without promising destiny, by protecting time for practice if it brings meaning, and by reminding everyone that improvement usually comes from hours of work riding on a brain temporarily tilted toward detail, not from a lightning bolt that replaced the person who was. The scientific frontier remains open, which lesions increase literal processing reliably, which neurochemical shifts predict a turn toward art or numbers, and can safe, reversible stimulation plus training coax a fraction of this effect in healthy brains for limited periods without side effects. Early results are tantalizing but uneven, and that inconsistency is itself a teacher. The brain is not a switchboard with a single genius lever. It is an ecology where reducing one species can let another bloom, and outcomes depend on timing, terrain, and how you cultivate the garden afterward. The soft closing keeps ore grounded. Sudden savant abilities after injury reveal that human potential is not a single ladder you climb, but a set of paths you light by how attention and inhibition are tuned. Injury sometimes tragically knocks down the gatekeepers, and a surprising path glows. The task then is to honor both truths, that cost and that opening, by supporting the person who walks it, using their new focus to build work and meaning, and exploring with care what their story teaches the rest of us about how many ways a mind can be clever. TMS temporarily rewiring personality. You sit in a chair, a figure-8 coil clicks by your temple, and a fingernail-sized region of cortex feels a flutter you can't quite name. And the claim that follows in headlines, that TMS rewires personality, is both too dramatic and not dramatic enough. The steady way in is to see transcranial magnetic stimulation as a precise, causal nudge to a living network that can shift your default ways of feeling and choosing for minutes, hours, and in some regimens, weeks. Not by overwriting who you are, but by retuning the weights on circuits that make traits show up as habits. Begin gently with what's real in the physics and the body. A rapid pulse of magnetic field induces tiny currents in targeted tissue a couple of centimeters beneath the skull. Depending on the pattern, single shots, short trains, or repeated bursts at particular rhythms, you can make that patch more or less likely to fire with its neighbors for a while. And because brains are not a bag of isolated parts but a set of tightly coupled loops, local modulation can ripple into the networks that underwrite mood, attention, patience, social judgment, and confidence. History matters here. For decades, psychology mostly correlated behavior with brain activity. TMS let researchers press a button and watch behavior change, turning "this area lights up when you do X" into briefly quieting this node reduces X, or tickling this node boosts X, which is how we learned that left prefrontal stimulation can ease low mood, that targeting right parietal junction can tilt moral judgments about intentions versus outcomes, that pre-SMA pulses can change how often people stop themselves mid-action, and that nudging dorsolateral prefrontal cortex, the workhorse of control, can make you more or less willing to wait for a larger later reward instead of grabbing a smaller, sooner one. None of these effects are magic. They're shifts in thresholds across loops, default mode, salience, and control networks that, when you string them together across days as in clinical RTMS protocols, add up to something that looks remarkably like a trait drifting, irritability softening, rumination loosening, curiosity flickering back on, risk appetite sliding a notch, social caution easing. Development gets clearer when you zoom in on timescales, because rewiring is a slippery word. A single high-frequency train over prefrontal cortex can increase excitability for a half hour or so. A low-frequency train tends to dampen it for a similar window. Patterned bursts, like theta burst, can push longer. Do this once and you've changed state. How your networks coordinate today. Do it daily for several weeks and dendritic spines and receptor balances inch along in the background, so that when the external driver stops, the new coordination can persist. Now you've nudged trait, not by replacing your personality, but by making certain responses more available and others less sticky. That's why people in treatment report not, "I became someone else," but "the same hassles don't hook me as hard. I answer instead of snap. I can stay with a problem long enough to finish," or "I feel like talking to friends again." And it's why lab volunteers under carefully blinded, sham-controlled setups can show measurable, reversible shifts in fairness judgments in a bargaining game, in appetite for risk on gambles, in willingness to punish cheaters, or in confidence in their answers on hard perceptual tasks. All the small cogs from which personality is assembled over weeks and years. Safety belongs in the same breath as power. Modern coils and dosing rules make TMS one of the safest causal tools in neuroscience. Ear protection for the clicks, rare headaches after sessions, vanishingly rare seizures in screened patients. But the very fact that a coil outside your head can tug on patience, empathy or boldness carries an ethical charge. So good teams predefine goals, reduce disabling rumination, lift anhedonia, and measure function rather than vibes, resisting the Silicon Valley fantasy that you can dial in more charisma at lunch. Mechanism is where the fascination deepens without hype. TMS does not press on or off in a blob. It perturbs timing and gains in microcircuits, shifts oscillatory synchrony, and changes how much a top-down prediction can suppress a bottom-up signal. In a discouraged brain, control regions may be undercoupled to salience hubs that yell, "This matters." So every small stressor floods experience with urgency, race, prefrontal coupling for a few weeks, and the same events arrive as manageable. In an anxious brain, the amygdala network may bias toward threat interpretations. Pace the prefrontal limbic dialogue, and reappraisal becomes less effortful. In someone who leans hard toward immediate reward, boosting the nodes that keep time in working memory makes later feel less abstract. These are not speculative cartoons. They're the sort of changes you can watch with concurrent EEG, oscillations retuning after a train, with fMRI, connectivity patterns normalizing toward healthy controls, and in behavior, delayed discounting curves flattening, go-no-go errors dropping. If you want to know whether TMS can change who you are, the sober answer is that it can temporarily change what is easy for you to do. And what is easy becomes what you do often, and what you do often becomes the story you tell about yourself. That's close enough to personality for both excitement and caution. There are subtleties worth learning if you're going to reason rather than react. First, place matters. A centimeter error can swap networks. Modern clinics use neuronavigation from structural scans to land on the same spot across days, not forehead landmarks alone. Second, protocol matters. Frequency, train length, and intervals can push excitability up or down. Theta bursts can mimic hours of higher frequency trains in minutes for some targets, but not all heads respond the same. And state dependence is real. You get different results if you stimulate while someone is attending, remembering, or mind-wandering. Third, expectation matters. Sham coils can produce tingles and clicks. Good studies keep participants and raters blinded. Even then, placebo can amplify genuine plasticity, which is fine in a clinic. Feeling hopeful helps you practice new habits, but must be separated in research. Fourth, transfer matters. A session that shifts fairness judgments in a toy game does not automatically make you better at negotiating rent. Bridging lab changes into life means pairing stimulation with the behavior you want. Cognitive therapy, exposure, habit practice. So the newly pliable circuits wire in a direction you choose. Finally, equity matters. If tools that nudge patience or social ease become widespread, we owe thought to consent, access, and misuse. No one should be coerced into performance tuning. And the line between helping a stuck mind and sculpting a convenient citizen depends on who sets the goal. The practical close is softer than the headlines, but more useful in the long run. TMS is a way to make the brain briefly more rewritable at a chosen address. Used with care, it can give a depressed person back their curiosity, an anxious person back their slack, an impulsive person a longer fuse. Used thoughtlessly, it's a clicky parlor trick that proves we can push buttons without asking why. The adult way to carry this is to see your personality as a set of well-worn paths that biology, history and practice built together, and TMS as a chance to add a switchback where the climb got too steep. Then walk it daily until the new route feels like you. Placebo surgeries working as well as real ones in trials. A scalpel slice, a bright light, the hush of a masked team, monitors murmuring like a lullaby. And here is the unsettling claim that has shaken modern medicine more than most. In carefully run trials for certain pain and mobility problems, patients who received sham surgery, anesthesia, small incisions, the full theatre of care but no therapeutic maneuver, often improved just as much as those who got the real procedure, which doesn't mean surgery is make-believe. It means that the ritual around it is pharmacology in disguise, and that our bodies respond powerfully to meaning, expectation, and time when the condition at hand is one that waxes, wanes, and listens to the brain. Begin gently with what actually happened, not rumor. In a landmark trial of arthroscopic surgery for knee osteoarthritis, volunteers were randomized to debridement, lavage, or a sham procedure in which the surgeon made skin incisions and simulated the sounds and steps without touching the joint. Months later, pain and function scores rose in all three groups, with no advantage for the real operations. Walking distance, stair tests, night pain, all the measures patients care about most. Teaching that for worn cartilage, the scope's theatre carried as much power as the shaving of frayed tissue. Similar stories repeated elsewhere. In vertebroplasty for painful osteoporotic fractures, people assigned to a sham, local anesthetic, pressure, chatter, but no cement injected, reported pain relief comparable to those treated for real. In shoulder impingement, trials that compared full decompression of bone spurs to diagnostic arthroscopy alone found little difference in outcomes. In degenerative meniscal tears, patients randomized to partial meniscectomy versus sham arthroscopy improved about the same, especially when the tears were age-related and not caused by acute locking injuries. None of these studies show that surgery never works. When a bone is broken through, a tumor compresses a cord, an appendix threatens to burst, the scalpel saves life or prevents catastrophe, but they do expose a category of procedures aimed at chronic pain and function, where the act of being operated on carries a healing payload independent of the mechanical change. Development deepens when you ask why the sham helped and what that says about you. Part of it is expectation. Anesthesia and the operating room are the most potent placebos our culture knows, and the brain's pain circuits are tuned by belief. When you expect relief, the brain releases its own opioids and dopamine, dampening pain and lifting mood in ways you can block pharmacologically in lab settings, which is strong evidence that chemistry follows meaning. Part of it is natural history. Many musculoskeletal pains flare and subside on their own. People seek surgery at the peak of misery and would have improved somewhat regardless. That statistical pullback toward average misleads both doctors and patients. Part of it is attention and care. Pre- and post-operative physical therapy, rest, protected activity, a clinician who calls to check on you, a family that treats you as healing. These are active ingredients. When the sham group receives the same schedule of therapy, the same brace, the same follow-up, the placebo isn't nothing. It's a bundle of all the non-incision parts of medicine that we usually forget to count. Part of it is measurement. Outcomes like pain, function, and quality of life are real, but subjective. They are exactly where meaning and support exert the largest effects. So trials must be blinded, or we risk mistaking gratitude and hope for a unique surgical benefit. And part of it is mechanism. A degenerative knee often hurts because of inflammation and central sensitization, rather than snagging debris. Washouts and shavings cannot change the biology driving those signals, but time, movement retraining, strength, weight loss, and confidence can. To hold this topic honestly, you also have to step into the ethics, because sham surgeries are not pills. They involve anesthesia risks and incisions, which means you don't run such trials unless the community truly doesn't know if a procedure works. Equipoise. Unless you minimize risk and unless consent is meticulous. The best trials did this. They told volunteers they might receive anesthesia and skin cuts without therapeutic action. They kept data collection teams blind to allocation, and they predefined what counted as success before the first person rolled into the room. Only with that discipline could they give us knowledge strong enough to change practice. And practice did change. Many guidelines now recommend trying structured physical therapy, strength and neuromuscular training, weight management, and pain education ahead of routine arthroscopy for wear and tear knee pain. Vertebroplasty indications narrowed, steering toward carefully selected cases with strict imaging and timing. Subacromial decompression waned as a first-line fix for broad impingement, with emphasis shifting to targeted rehab and, when necessary, procedures with clearer mechanical logic. Keep the balance. There are surgeries for pain with huge objective gains, joint replacements for end-stage arthritis, transform walking distance and night sleep in ways no sham can match. Coronary bypass for certain patterns of blocked arteries relieves angina robustly. Decompression for a herniated disc with progressive weakness can restore function quickly. And in oncology, cutting out a tumor is not a placebo. But whenever a proposed operation aims to soothe a chronic ache without correcting an urgent mechanical fault, the placebo surgery literature asks you to slow down and demand strong evidence. How do you carry this into your own decisions without cynicism? Ask your surgeon precise questions. For people like me, what is the absolute chance of meaningful improvement at 3, 6, and 12 months with surgery versus an optimized non-surgical plan? Has any sham-controlled trial been done for this procedure and condition? And if so, what did it show? What are the risks if I try rehab first for 12 weeks? Will I miss a window where surgery works better? Which parts of your post-operative plan could we start now? Education, strength, gait retraining, so that I harvest the benefits whether or not I ever go to the OR. Ask for numbers, not vibes. Ask for alternatives that change the biology. Sleep, graded activity, inflammation control, because those are the levers that sham trials accidentally revealed as powerful. If you're a clinician, take the gentler but harder path of building rituals of care outside the theatre. Predictable follow-ups, clear explanations that reduce fear. Catastrophizing amplifies pain. Programs that measure progress weekly so patients see gains they would otherwise miss. The same attention that makes an incision feel medicinal can be redirected toward coaching, with fewer risks and often longer-lasting results. If you're a researcher, honor the courage of those who volunteered by designing the next generation of trials with even cleaner methods. Pre-registration, patient-centered outcomes, sham controls were ethical, and long enough follow-up to capture both the early glow and the late reality. The soft landing is not an attack on surgeons. It is a vote for humility and measurement. The knife is brilliant for fixing broken mechanics, but for some aches and degenerations, the theatre around the knife carries as much medicine as the cut. When you recognize that, you do not surrender to illusion. You upgrade your care, saving surgery for the problems it truly solves and pouring the power of meaning, expectation, and guided movement into the many it does not. The third man factor, sensing a presence. When alone in danger. You are alone on a ridge where the wind peels sound from stone. The air is thin enough to sting, and a thought you did not plan arrives with the firmness of a hand on your shoulder. You're not alone. Keep moving. Step here. And the careful way to enter the third man experience is to respect both its power and its plausibility. People in mortal stress do sometimes sense a steady companion who guides or comforts them. And the best explanation is not angels versus delusion, but a social brain keeping you alive by borrowing the shape of a person when your internal signals, your environment, and your expectations fall out of sync. Begin gently with what survivors describe across mountains, deserts, shipwrecks, collapsed mines, and burning buildings. The presence is calm rather than dramatic, close but just out of sight, sometimes with a voice but often only a felt nearness, offering simple, actionable advice. Slow down, rest behind that rock, turn left at the next cairn. And when the danger passes, the feeling fades like a dream that leaves its wisdom behind. The development becomes useful when you grasp how many converging pressures push a lonely brain toward companionship. Under extreme threat, stress chemistry floods the system. Adrenaline, cortisol, surges of norepinephrine, while blood sugar runs low, oxygen dips, sleep collapses, and temperature slips. Each of these alone can warp perception, but together they nudge a predictive brain, one that constantly guesses what's happening and then checks the guess against incoming signals, into a brittle, high-gain mode where errors are costly and missing a cue could kill you. Your body budget announces deficits from the inside, pounding heart, tight chest, dizzy sway, and your senses report chaos from the outside. White roar of wind, featureless snow, flicker of headlamp on dust, and the model that usually stitches body and world into me, here, now, wobbles. The social layer of your brain, built to track where other people are, what they intend, and how to coordinate with them, is one of the strongest stabilizers you have. It lives in networks that include the temporoparietal junction, tagging self versus other, the insula, reading internal state, and prefrontal hubs, setting priorities and rules. When the loop tries to predict who is guiding me and finds only the thinnest traces, memories of a mentor's tone, the posture of a trusted partner, the rhythm of a climbing rope once felt through gloves, it can fill in the missing person, not as theatre, but as an emergency control strategy. Externalizing part of your inner monologue into a companion lets you divide attention. One voice watches footing, the other scans the sky. One voice breathes, the other counts paces, and that division reduces cognitive load exactly when load would drown you. There is a second, subtler ingredient: sensoromotor mismatch. Experiments have shown that when you perturb the timing between your movements and the tactile feedback you expect, a robot applies a delayed touch to your back as you move your hand, or your footsteps echo in an odd rhythm. Healthy people can feel a presence just behind them, a shadow self that the brain treats as not me. In wild places, nature supplies these mismatches. A gust shoves you half a beat after your foot falls. Fog blurs the boundary between your headlamp and the horizon. The crunch of ice answers your steps with a lag. Your mapping system, tuned since infancy to keep track of other bodies, interprets the lagging copy as another agent. Add isolation, days without conversation, weeks without shared decision-making, and the brain's hunger for social prediction will literally hallucinate a partner to synchronize with. The way a metronome left alone will latch onto the hum of a refrigerator. None of this flattens centuries of testimony. It gives it contour. Consider what the third man tends to say. Fewer words than your usual self-talk, more directive, less ruminative. That's your control network stripping language to its utility under pressure. Consider when it appears. At the crest of exhaustion, during whiteouts, at night in featureless terrain, inside smoke, situations that starve you of the sensory anchors your brain uses to tie a self to a place. Consider who it feels like: a deceased friend, a stern coach, a rescuer in uniform, figures your memory has tagged as reliable. The brain is doing what it always does, only harder and with the volume up. It builds a guide from the most trustworthy templates on hand. There are edge cases worth knowing because they sharpen, not blur, the picture. In bereavement, many people feel the presence of a loved one in the weeks after a loss. In solitary sailing and polar travel, adventurers report companions during storms or monotony. In neurology clinics, patients with certain lesions or seizures describe a shadow person at the edge of sight. And in sleep-deprived, hypothermic or hypoxic soldiers, medics have documented brief instructive voices that vanish with rest, food or oxygen. Across these settings, the probability of a presence rises with deprivation, mismatch and isolation. It falls with restoration and social contact. And crucially, most third-man episodes are helpful rather than terrifying, unlike psychotic voices, which often harass or threaten, because the context and the person's prior beliefs aim the model toward protection. Knowing this lets you prepare without cynicism. If you work or play where the margin is thin, alpinism, blue water sailing, firefighting, caving, assume that your brain's social machinery will come online to help you when inputs go sparse. Treat it as a safety feature, like a reserve parachute that needs training. Before expeditions, build a simple voice script with your team. A handful of phrases that encode priorities. Slow is smooth, smooth is fast. Hydrate, rest, decide. and pair them with breath counts or paces so they become embodied. In the field, when a presence arrives, you don't have to argue about its metaphysics. You can ask of any directive the question you would ask a teammate. Is this specific, feasible, and consistent with our plan? If yes, follow it. If no, pause, eat, check the map and compass, and seek redundancy before acting. Protect your body budget early. Warmth, calories, water, sleep, because deficits are gasoline on the hallucination engine. Treat oxygen and sugar as cognition tools, not just comfort. Carry social cues in your kit. A recorded voice from home with the exact cadence you're used to. A short letter to your future self sealed for storm days. Even a photograph placed where you will see eyes looking back. These anchors can feed the same networks that the third man recruits, with more control. In organizations, bake the phenomenon into training. Teach recruits that sensing a presence alone in a fire or collapse is common and can be helpful. Teach them the red flags that mean it's becoming unsafe, commands to do something off-plan and irreversible, contemptuous or shaming tones, disorientation, and the antidotes: pause, touch a stable surface, say aloud the next 3 steps. For clinicians, there's a broader lesson. Presence hallucinations are not automatically a sign of disease. In the right context, they are a sane brain's social prosthesis, and the humane response is to validate and integrate rather than pathologize what helped someone live. The soft closing allows awe without surrendering clarity. The third man factor doesn't prove a hidden companion walks us through blizzards, and it doesn't reduce survival to a glitch. It shows that the mind we carry into risk is layered with safeguards, one of which is so deeply social that in the emptiest places, it will conjure a steady other to share the load. If you leave with one upgraded habit, make it this: tend to the conditions that keep your model of self and world in register, and when a calm presence appears at the edge of your vision in a hard hour, let it be what it likely is: your best self wearing a face you trust, reminding you to breathe, to choose the next good step, and to keep moving until the ridge lowers and the wind finally gives you back your own voice. Collective false memories. Mandela effect in controlled groups. You remember it clearly because everyone else does too. The cereal logo with the extra loop. The line in the movie everyone can quote. The costume color that obviously was blue. And the unsettling truth is that shared certainty is one of the easiest things to manufacture on purpose, which is why the Mandela effect isn't just an internet parlor game, but a live lesson from controlled experiments about how groups grow the same false memory together. Not because people are gullible cartoons, but because memory is a living reconstruction built from gist, expectation, and social signals, and those ingredients are often identical for everyone in the room. Begin gently with how your own recall works before a group ever touches it. When you encode an event, you don't store a video. You store fragments, the general meaning, the gist, a few vivid details, verbatim traces, the source, where, when, who told you, and your feeling tone. Later, when you retrieve, you rebuild the scene from those pieces and whatever templates, schemas, you carry for how these things usually go. This is efficient and usually accurate, but it has 2 reliable failure modes that become contagious in company. First, when gist is strong and verbatim detail is weak, your mind will fill a blank with the most typical missing piece. In classic lab tasks, people read lists like bed, rest, pillow, dream, and later confidently remember the word sleep, which never appeared. An error so predictable that researchers can induce it in most of a class at once. Second, source monitoring, the skill that tags where a detail came from, slips under pressure or delay, a hint you imagined, a joke a friend made. The caption under a photo can be misfiled as something you witnessed. Now place that reconstructive machine inside a group and watch the social physics tilt the table. When you and peers discuss an event, several forces act at once. Conformity pressure, subtle, not the cartoonish kind, makes you weight others' confident reports more than your own hesitation. If someone across the table asserts the thief wore a red cap, your brain treats that as new evidence and your retrieval tilts to search for redness, often finding a trace, a fire engine in the background, a stop sign, and weaving it in. Memory conformity, the specific phenomenon where one person's recall shapes another's, has been demonstrated by showing pairs slightly different videos, say, one angle reveals a wallet, the other does not, and then letting them chat. Afterward, both remember the wallet, and the error spreads fastest when the confederate sounds certain, appears knowledgeable, or agrees with you on unrelated topics first to build rapport. Add the misinformation effect. After an event, a single leading question, how fast were the cars going when they smashed, or an authoritative slide with a mislabeled object, can shift not just your answers, but your sensory memory for what you saw. In groups, the same questions and labels are broadcast, so the same bias is injected into everyone's reconstruction in parallel, which is why entire classes can recall a non-existent stop sign where a yield sign stood, or see broken glass that was never on the road. The internet supercharges these lab ingredients. A high-fidelity mock-up of a logo with one letter altered, reposted thousands of times with comments like, "We all remember this, right?" gives millions the same wrong exemplar and the same social proof. Later, when you try to retrieve the brand from memory, your mental vote counting favors the version you have most recently seen endorsed by many, and your confidence rises because confidence tracks fluency. How easy it felt to retrieve, not truth. Confidence, in turn, is contagious. Groups equate firm tone and fast recall with accuracy, so the smooth storyteller becomes the de facto archive, and dissenters self-censor, depriving the group of the very noise that would have preserved the truth. Development becomes useful when you move from mechanism to measurement and tactics. In controlled settings, researchers can make a roomful of people misremember in the same way by 1. Seeding them with the same misleading detail, or 2. Letting them discuss freely, and 3. Testing later with questions that reward gist over detail. Shift any of these, warn in advance that misleading info will appear, separate witnesses before they talk, or ask for free recall before recognition, and the collective error shrinks. That teaches you practical defenses. If you must remember together, after an incident in a lab, at work after a mishap, start with independent written accounts before any group debrief. This preserves each person's verbatim fragments before conformity can homogenize the pool. In meetings, appoint a detail advocate to ask, what exactly did we see? What did we infer? And to capture uncertainties without shame. Labeling a memory as tentative protects it from hardening merely because it was said aloud. When reviewing media claims, check the source tag. Did you remember the scene from the original film or from a meme? Was that quote printed on a poster you love? Your brain is generous with credit and will reassign authorship to the most emotionally salient source unless you force it to anchor. If you teach or run investigations, structure procedures to resist memory contagion. No leading questions, staggered interviews, careful documentation of who said what first and, when possible, presentation of materials that are exact copies of originals rather than enhanced versions that smuggle in edges and color. There are subtler levers too. Delay sharpens gist and blurs detail, so if you want accuracy on specifics, collect accounts quickly, yet not so quickly that stress drives guesses. Arousal narrows focus, which can help you encode a weapon at the cost of the suspect's face. So later, ask yourself openly which parts you actually saw and which parts you know from schema. Robbers wear black beanies. And there are uncomfortable but liberating truths to keep handy. First, collective false memory is not proof of a glitch in reality. It is proof that humans share priors, formats, and channels. So when the same template meets the same noise, the same beautiful error falls out. Second, your feeling of, "I've always known it this way," is mostly a property of today's retrieval. How coherent the reconstruction feels now, not a diary check on your childhood. You can respect the feeling without mistaking it for a timestamp. Third, disagreement is a public good. One person saying "I remember it differently" is not friction to remove, but information that the room's gist has run ahead of its verbatim anchors. The soft landing is not to become a cynic who trusts nothing, but a better custodian of how truth forms in groups. Treat memes and mock-ups as delicious but sticky confounds. Write first, talk second. Demand sources when everyone nods too fast, and build rituals that protect detail before the story hardens. If you leave with one upgraded habit, Make it this. When you and your friends all remember the same wrong thing, don't feel embarrassed. Feel curious about the machine that made the same beneficial shortcut for everyone, and then adjust the inputs next time so the shortcut lands closer to the truth. Blind people navigating rooms. Using clicks. You hear it before you understand it. A crisp tongue click. Sharp and brief like a raindrop on metal, and in the half second that follows, the room answers. A soft bloom if the space is wide. A quick, bright return if a wall is near. A dry hush if fabric soaks the energy. A thin, metallic ping if a chair leg hides just off your path. The careful way to enter how blind people navigate rooms using clicks is to treat it not as a party trick or a mysterious sixth sense, but as a learnable craft built on physics you already use without noticing, disciplined attention to timing and timbre, and a brain that will gladly reassign idle circuits to decode echoes when vision steps back. Begin gently with what the click is doing. A good navigation click is short, tens of milliseconds, so it doesn't smear into its own echo. It's rich in high frequencies so edges and small objects reflect it. And it comes from a consistent spot, the tongue against the palate or the teeth, so the brain can treat the outgoing pulse as a ruler. When that pulse leaves your mouth, it sprays the room, hits surfaces, and returns with hints. Delay carries distance, loudness hints at size, and the frequencies that get absorbed or boosted tell you about material. Curtains sip the highs, glass throws them back, wood rounds them a little. Your two ears add geometry without any math lesson required. A return that reaches the right ear a hair earlier and louder pulls the perceived source rightward. A return that brushes both ears together with the same timing feels centered. If you subtly turn your head while clicking, tiny figure eights with your chin, you make the world answer from slightly different angles, letting your brain triangulate objects the way a bat does, only slower and with human patience. Development deepens when you realize how much structure lives in an ordinary room for the ear to read once you decide to listen for it. Doorways act like acoustic funnels. Clicks fired down a hallway arrive back smooth and confident, while clicks toward an open doorway thin out and spread, as if the air itself had less to grab. Corners announce themselves with layered returns. First one wall, then the other, then a faint third from the far diagonal. So a practiced listener hears a shape, not just a bounce. Table edges create acoustic shadows on the floor, a quiet wedge behind the lip that gives away both height and overhang. A cluster of chairs produces a comb of little nulls as their legs steal specific slivers of the spectrum, which is why some echolocators can tell a pushed-in chair from an open space even when the room is loud. Your own body becomes a probe. Click while you slide a foot forward, and the subtle change in echo from the floor tells you how close your toes are to the base of a wall. Click as you sweep a cane, and the cane's tap rings differently near obstacles, because resonant cavities shift the tail of the sound. The brain learns these pairings by repetition, not by formulas. You click. You confirm with a hand or cane. You click again, and over weeks the what if narrows into I know. Neuroscience adds an inspiring twist without mystifying the process. In people who rely on tongue clicks for navigation, the parts of the brain that incited life process edges and spaces light up to the sound of their own echoes, as if the auditory scene has been promoted into a kind of spatial picture. That doesn't mean hearing becomes seeing. It means the cortex is pragmatic. It will recruit idle real estate to whatever job matters most. And if mapping the world by sound is the job, then edge detectors that used to care about lines on a page will learn to care about sharp transients in air. The craft is not mystical, but it is methodical, and here is how it looks in practice when done well. Experienced echolocators don't click constantly. They pulse when the question matters. Doorway or wall, open chair or occupied, clearance under the table or no. They adjust click strength to the range they care about. Softer in clutter so as not to drown in echoes, sharper across a lobby. They use head movement and micropauses to let the first reflections arrive cleanly, before the room's longer reverberation muddies the picture. And they combine echolocation with the tools that always belong to the blind traveler's kit. a long cane to guarantee safe contact at ground level, trailing fingers on a wall to confirm a corridor, even the scent and temperature shifts that announce a kitchen or an exit. The skill can be built in quiet places first, a hallway, an empty room, then transplanted to harder acoustics. Carpet and books make echoes faint. Tile and glass make them shout. Music and HVAC noise create masks that hide faint returns. Supermarkets are an advanced level because aisles produce long, smooth corridors punctuated by chaotic end caps that scatter reflections in confusing ways. The trick is to accept that some places will never yield fine detail, and to use grosser cues there, the open signal of a wide aisle while saving fine discrimination. For calmer spaces, counting chair legs in a quiet classroom, your clicks can even read motion. A person crossing a room sends back returns that shift with time. A moving notch in the frequencies you hear as their clothes, edges, and limbs change angle, which is enough to decide whether to pause and let them pass. Ethics and humility belong alongside technique. Blind echolocation is not a superpower, and it is not a replacement for tools and community. It is a trained extension of ordinary sensing that becomes beautifully reliable with practice and honest feedback. Not everyone will love the tongue click, so some use finger snaps, light foot taps, or brief tisk sounds. Each has trade-offs in volume and frequency content, and the quietest options suit quiet rooms but struggle against traffic. What matters is consistency and a willingness to calibrate. Make a guess from the echo, test the guess with touch or cane, store the correction. The social world can help or hinder. Buildings designed only for the eye are hostile to the ear. Endless soft surfaces that erase cues, chaotic soundscapes that drown them. Friendlier spaces have straight corridors, predictable alcoves, a mix of reflective markers and absorbent calm, and clear auditory beacons like gentle fountains near entrances or distinct floor textures at crossings. Even a simple choice like leaving a strip of hard floor along a wall can sharpen a corridor's acoustic rail for someone clicking as they walk. Safety and realism deepen respect for the craft further. Beginners should start with a guide. Inside a room they can map by touch and add clicks as a supplement. Early wins might be as small as hearing a doorway from 2 steps away or distinguishing a cabinet from a curtain. The route to confidence is 100 such wins, not a leap to bicycling by sound. Fatigue and illness dull discrimination. Hydration and rest sharpen it. Mouth dryness makes clicks inconsistent. Ear congestion blurs timing. These are small, predictable factors, so the wise traveler builds margins. Slower pace, more cane work, on low energy days. Technologies can sit beside the human skill without replacing it. Smartphone beacons to label doors, small wearable sonars for long hallways, bone conduction headsets that leave ears free for natural echoes. The point is not to hand hearing to a gadget, but to let tools handle the boring distances so your clicks can concentrate on the near and the delicate. The soft closing keeps wonder honest. A tongue click that sketches a room is not magic. It is the brain doing what it has always done, turning patterned energy into usable maps. And with steady practice, it can let you feel doorways open before your hand finds the frame, sense a chair before your shins learn it the hard way, and move through spaces designed without you in mind with a confidence that is quiet, efficient, and earned. If you leave with one changed habit, let it be this: treat sound as structure, not background, and notice how even your sighted walks grow richer when you hear rooms answer you back. Extreme strength during emergencies. A stranger's scream needles the air, a tire jack slips, and before you can think your body lunges, you hook fingers under a bumper that would normally defeat you. The metal yields a few centimeters. There's space for a trapped leg. And only later do you shake and wonder where that force came from. The steady way to enter extreme strength during emergencies is to keep both the awe and the anatomy in view. Because what people call hysterical strength is not magic muscle arriving from nowhere, but a rare alignment of physiology, physics, and focus that drops your internal brakes just long enough to trade safety margins for raw output. Start gently with the basics you carry into any crisis. Your skeletal muscles are capable of more force than you typically allow them to use. On ordinary days, your nervous system protects joints and connective tissue by keeping a lid on how many motor units fire together and how fast they discharge, and by letting pain, fear, and social caution nudge you to stop before structures fail. Think of it as an internal risk manager, sometimes called a central governor, blending signals from your spinal cord, tendons, and brain to ration effort. When emergency hits, child under a chassis, partner pinned under a beam, that governor changes its policy. Stress hormones spike, adrenaline surges within seconds, with noradrenaline and cortisol joining. Heart rate and blood pressure leap, breathing deepens, liver and muscle dump glucose, and sympathetic nerves sharpen nerve muscle transmission. Simultaneously, inhibitory reflexes that normally make you ease off, like those mediated by the Golgi tendon organs, are dialed down. Central drive from the motor cortex ramps up, and more motor units are recruited and fired at higher rates, which is why the same fibers that felt sluggish a minute ago can seem suddenly awake. At the same moment, perception warps usefully. Pain is gated at the spinal cord and modulated in the brain, so the sting that would stop you at the gym barely whispers. Attention narrows and time can feel viscous, which is not mysticism, but a change in how you sample and store events under high arousal. And threat-prioritized movement programs, push, pull, brace, rise to the top of your action stack, improving the chance that the force you do generate lands in a mechanically smart way. Add the physics you rarely notice, and some folklore cleans up. People imagine someone deadlifting a car, but vehicles often trap by distribution and geometry rather than pure mass. Lifting a bumper a few centimeters can be within human reach if leverage is favorable. Flexing the tires, rocking the frame, or lifting one corner reduces the load dramatically compared with raising the whole car. Rough surfaces add grip, adrenaline dries palms, and micro adjustments. Feet under hips, spine braced, elbows locked, turn intent into favorable vectors. In a crisis, your brain explores these options without waiting for a coach, because habit and reflex take the wheel. The development deepens when you look for evidence beyond headlines. In labs, measuring absolute voluntary strength is tricky because true all-out effort is rarely safe. But researchers can nudge the ceiling by delivering brief electrical or magnetic pulses to the motor system during maximal contractions. The extra force evoked by these pulses is a proxy for unused capacity, and it shrinks as arousal, motivation, or threat increase, meaning that in hot states your voluntary access to muscle grows closer to your actual ceiling. Startle reflexes, sudden loud sounds layered onto a go now cue, can increase rate of force development, as can anger scripts or highly motivating stakes. Caffeine and cold exposure shift similar levers, though not to emergency levels. Athletes train versions of this on purpose. Heavy isometrics, cluster sets, psych-up rituals, to recruit high-threshold motor units and speed neural firing. Yet even they keep a brake on to spare tendons and discs. A brake your survival systems will temporarily weaken if it thinks flesh is cheaper than a life. The flip side matters because it keeps the story honest. There are costs to overriding protection. The same episodes that make you proud can leave torn muscle fibers, strained ligaments, or herniated discs. In extreme cases, prolonged maximal exertion plus heat and dehydration spirals into rhabdomyolysis, a breakdown of muscle that floods the bloodstream with proteins the kidneys hate, and the connective tissue that anchors strength adapts more slowly than muscle. So a nervous system that suddenly allows everything can write checks. Tendons can't cache. There are also cognitive traps. Memory under stress is reconstructive, and stories pick the most cinematic angle. What felt like lifting a truck might have been lifting enough of one corner at the right moment, with a helper pushing from inside. Still heroic, but physics, not magic. None of this shrinks the phenomenon. It makes it teachable. If you want to be more capable when it matters, and safer, you can borrow the useful parts of the emergency recipe without waiting for disaster. First, learn positions that turn you into a better lever under load. Neutral spine, hips back, elbows stacked under wrists, feet making a tripod with the ground. Practice short, heavy isometrics, pushing a car that's in park, pulling against a fixed strap, bracing a doorframe, to teach your nervous system what hard, now feels like while your structure learns to share the stress. Second, train breath as a force multiplier. A quick breath in, a brief brace, like fogging a mirror with your mouth closed, and an open throat exhale through pursed lips. Let you transmit force without collapsing your ribcage or spiking blood pressure uncontrollably. In the wild, this looks like a tight hiss while you push. Third, rehearse simple scripts that command action without panic. Plant brace push. Hands here, feet there, lift 1 inch. Rock, don't yank. Under stress, language collapses to the simplest verbs. Make yours the right ones. Fourth, cultivate arousal range. The ability to turn on and then turn down. Because staying red-lined after the moment passes is where errors multiply. A handful of slow exhales with long, relaxed out-breaths. A quick shake of the limbs, and a check-in for pain or dizziness keep a rescue from becoming a second casualty. Fifth, respect the promise and the limit of self-talk. Anger can unlock force, but anger also narrows options. A practiced, firm, almost impersonal voice. Move the beam 2 centimeters, clear the airway, call for help now. Recruit strength without blinding you to safer tactics. Jacking, levering, removing debris. There are also community lessons hiding in these stories. Bystanders can upgrade outcomes by improving leverage rather than shouting for more muscle. Have one person wedge a board as a fulcrum while another pushes. Deflate a tire to drop a chassis. Roll rather than lift when possible. And coordinate with cadence. Push, 2, 3, brace. So bursts sync and don't cancel. A firefighter's or paramedic's calm tone is not just kindness. It's a metronome that organizes force. And there are design lessons. A low-cost lever kit in a public place can multiply human strength ethically, as can simple instruction placards near heavy hazards. Strength is not only in bodies, it's in environments that give ordinary people better physics under duress. Finally, there's the narrative you carry forward about yourself. It's tempting to romanticize the emergency version of you as the real one and to dismiss ordinary limits as weakness. The wiser reading is that you are a system with multiple operating modes, and the emergency mode is a legitimate, expensive gear that evolution installed for moments where tissue damage is an acceptable price. Honoring that gear means not trying to live there, but training enough structure, technique, and composure that when life shifts you into it, your effort lands cleanly, and the recovery is short. The soft landing keeps wonder intact without lying. Yes, people sometimes do what seems impossible because the brain lifts its safety caps and points effort through smart mechanics. No, that doesn't make 24/7 superhuman strength-wise or available on demand. The real upgrade is to let these rare bursts teach you how much of strength is coordination and context. To practice the few habits that raise your usable ceiling without courting injury. And to remember that the most heroic thing about emergency power is not the kilograms moved, but the precision and courage that aimed it where it saved a life. Cold plasma healing wounds. Faster, still not fully understood. A violet whisper flickers above the skin like a tiny aurora, cool to the touch and humming faintly. And if you're expecting cauterizing heat, you're already a step behind. Cold plasma is the paradox in your hand. A cloud of charged particles and reactive molecules created at room temperature that seems to coax stubborn wounds into moving again when they've stalled. Not by burning tissue away, but by nudging the microscopic conversations that make healing happen. The honest way in is to treat this as both promising and unfinished, because clinical teams are seeing real benefits in chronic ulcers and infected cuts, while scientists are still sorting out how best to aim the chemistry. Begin gently with what the stuff is. Plasma is often called the fourth state of matter, but here it's the mildest cousin. A puff of ionized gas, usually air, nitrogen, helium, or argon, energized by a carefully controlled electric field so that the resulting cocktail carries short-lived reactive oxygen and nitrogen species, think ozone, peroxide nitric oxide, a sprinkle of ions and electrons, a faint electric field and a whisper of UV. Cold means the average temperature stays near ambient, sparing living cells the thermal damage you'd expect from a spark. Engineers deliver it 2 main ways. A dielectric barrier discharge device that creates the plasma right above the skin, or a small jet that blows the plasma plume from a pen-like tip. Either way, you're painting a wound with a micro-weather system that lasts milliseconds and then collapses into ordinary air and saline. Now the puzzle turns practical. Why would bathing a wound in such ephemera help it close? Part of the answer is antimicrobial force without a scalpel. Bacteria, especially those in gluey biofilms that laugh at antibiotics, hate the reactive burst. The radicals puncture membranes, oxidize proteins, and disrupt the extracellular matrix that anchors colonies. And because the hit is chemical chaos rather than a single enzyme target, resistance is harder to evolve. Fungi and some viruses take a similar beating. But if sterilization were the only trick you could just wipe with bleach, the interesting part is that surrounding human cells tolerate and sometimes benefit from the same exposure when dosed correctly. Low, pulsed doses of reactive species nudge signaling pathways you already use for healing. Brief oxidative stress switches on transcription factors that upregulate growth factors and cytokines. Capillaries sprout more readily, angiogenesis, under a little nitric oxide encouragement. Keratinocytes at the edge of the wound proliferate and migrate faster. Fibroblasts reorganize collagen with more purpose. And macrophages, the immune system's project managers, shift from a pro-inflammatory stance toward a pro-repair one. Add a pH micro tweak. Plasma often acidifies the surface slightly, which discourages pathogens and favors tissue enzymes. And a gentle electric field at the wound margin, which appears to reinforce the body's own injury currents that guide cell movement. And you start to see why clinics report that stalled wounds look less angry and more granular in the days after treatment. Development gets concrete when you step into the wards that care for ulcers that won't quit. Diabetic feet with poor perfusion, venous leg ulcers with biofilms that laugh at silver dressings, pressure sores that have watched months pass. In small but growing studies, regular plasma sessions, minutes per visit, a few times per week, alongside standard care like debridement, compression, or offloading, are associated with lower bacterial counts, reduced odor, less exudate, and a faster march of epithelial edges. Patients report less pain on dressing changes, and nurses find less slough to battle. Surgeons like that, the devices don't add heat or leave residues. Infection control teams like that. The plume dissipates into air rather than building up antimicrobial chemicals in the tissue. Patients like that, it feels like a cool breeze rather than a cautery sting. None of this means miracle. Some wounds remain stubborn because the deeper problem, ischemia, uncontrolled glucose, pressure, still dictates outcomes. But the signal is strong enough that regulators in parts of Europe have authorized specific devices for dermatologic uses. And hospital protocols are being rewritten to include plasma alongside sharp debridement and meticulous dressings for certain indications. To keep your skepticism healthy, you should ask what we still don't know, because the unanswered questions are where poor practice hides. Dosing is messy. How much plasma isn't like how many milligrams. It's a moving target made of distance, gas type, pulse frequency, exposure time, humidity, and wound geometry. Too little and you get theatre, too much and you can injure cells, delay epithelial bridges, or irritate fragile granulation tissue. Not all devices make the same cocktail. A helium jet and an air DBD produce different ratios of species, different fields, different UV. Studies don't always report these details, so meta-analyses can mix apples and meteors. Most trials to date are small, sometimes unblinded, and often layered on top of aggressive standard care that itself was inconsistent before plasma arrived. Teasing out what portion of the gain belongs to the plume versus better offloading, better compression, or simply more attention takes stricter design. Long-term safety looks good so far. No signal of mutagenic trouble at clinical doses, and the UV component is tiny compared to sunlight. But the community keeps watch, especially for repeated use over months in older skin. You should also keep your eye on the psychology around any new instrument in medicine. When a tool looks futuristic and gives the caregiver something active to do, placebo-adjacent benefits, more frequent assessments, more careful dressings, more hope, ride along. Those are not fraud. They are the ritual side of care. But trials must control for them if we want honest effect sizes. Ethics and practicalities fit in the same kit. If you run a clinic, the right move is not to replace the fundamentals with violet glow. It's to add plasma to a disciplined pathway. Diagnose the cause of the wound: arterial, venous, neuropathic, pressure. Correct what you can. Revascularize, compress, offload, rotate, clean precisely. Then dose plasma with a documented protocol that specifies device, settings, standoff distance, pass pattern, and time. Photograph, measure, and culture at intervals. Stop if the wound declares itself allergic to the schedule. If you're a patient or caregiver, ask for numbers, not mystique. What's the expected change in area or bacterial load by week 4? How will we adjust if the wound plateaus? Which parts of my routine, nutrition, smoking cessation, glucose control, matter most to let this chemistry help? If you're a researcher, design the missing studies. Head-to-head devices with standardized outputs, dose-response curves by wound type, blinded assessors, and endpoints that match what patients care about. Days to closure, infection recurrence pain, not just surrogate lab metrics. There's also a frontier where engineering meets biology that you, as a curious mind, can watch with justified excitement. Tuned plumes that emphasize nitric oxide delivery for ischemic edges, or that stack brief bursts with rest periods to maximize signaling while minimizing stress. On-device sensors that monitor the actual species landing on tissue. Dressings impregnated with plasma-activated saline to extend the chemistry's tail for hours after a session. And combinations with low-frequency ultrasound to break biofilms mechanically while plasma finishes the job chemically. The soft landing keeps your wonder clean. Cold plasma doesn't heal by magic, and it isn't a cure-all, but it is a clever way to deliver microdoses of the same molecules your immune system and endothelium already use to talk, packaged in a form that kills microbes, quiets runaway inflammation, and prods repair without heat. When you frame it that way, the spectacle fades and the logic sharpens. Treat the cause, measure the response, respect the unknowns, and use the glow as a nudge that helps a stuck wound remember how to become skin again. Precognitive intuition. Knowing something is wrong. Seconds before it happens, a chill slips through you before the glass actually shatters. A whisper of "something's off" arrives in your chest a beat before the car in the next lane swerves. And the responsible way to enter precognitive intuition is to keep your footing on 2 truths at once. You are a prediction-making animal whose brain is constantly forecasting the next half-second of life. And in noisy, fast environments that forecasting can feel like a warning from the future while still being built from signals. Some so faint you don't notice them, some coming from inside your own body that arrive just in time. Begin gently with the machinery you already carry. Perception is not a camera. It's a guess that the brain refines using the blur of what's hitting your eyes and ears, plus a library of what usually happens next. That library is updated every time you drive, cook, play sports, scroll a feed, or argue with a friend. When conditions are stable and your experience is deep, those guesses become fast and quiet. A firefighter feels a living room wrong and orders their crew out moments before a flashover. A chess player moves a rook without computing every branch because their midbrain has seen this trap 1,000 times. The feeling we call a gut alarm is often your predictive engine spotting a pattern in micro cues. Hairline deviations in a driver's lane position, the way voices dampen in a crowd just before a surge, a shift in wind and odor before a pan flares that your reflective mind hasn't articulated yet. Your interoceptive system, the one that monitors heart, lungs, gut, skin, is wired tightly to attention, so tiny changes in your own pulse or breath amplify the sense that something external is about to break. In lab settings, you can see shadows of this. Skilled athletes show subtle anticipatory muscle priming before an opponent's move based on shoulder angle and timing. Seasoned investors' bodies, heart rate variability, skin conductance, shift milliseconds before they consciously judge a chart because they've internalized which shapes often precede a drop. Air traffic controllers' performance improves when their training emphasizes pre-event cues rather than post-event reactions, teaching the body to lean toward the next likely state. This is not magic, it's compressed experience leaked into the present as a feeling. Development deepens when you address the spikiest claim head-on. reports that people show physiological changes seconds before a random future event. Sweaty palms before a startling image chosen by a computer, for example, have circulated for years under names like presentiment. The careful read is that the literature is mixed and fragile. Some studies report tiny anticipatory effects at the edge of measurement. Others fail to replicate when pre-registration, better randomization, and stricter statistics are used. Publication bias, positive results getting printed more than null ones, timing artifacts, subtle rhythms in devices and participants, and expectancy effects. Participants, unconsciously learning the experiment's pacing, can mimic a peek ahead. Skepticism is not cynicism here. It keeps you from overfitting noise, but skepticism also leaves room for what is solid. When events are not random, your body can legitimately get there first. And in real life, the world is almost never random. Hazard unfolds with telltale signatures. A drunk walker's sway shifts before they stumble. A pot's steam thins a second before it boils over. A family member's voice tightens a syllable before an outburst. In all these, your sensory system samples faster than your storyteller can speak, and evolution gave the body veto power to jolt you towards safety before a sentence forms. There's also the math of mistakes to consider. When the cost of a miss, you ignore the twinge and collide, dwarfs the cost of a false alarm, you break and feel silly. Biology biases you toward early warnings. Your error management strategy is tuned to err on the side of caution in lopsided games, so you will feel more premonitions than genuine hits, an annoying feature in calm times, a life-saving one at speed. Practically, you can turn this from folklore into a skill without telling yourself stories about time. First, build a vocabulary for your own signals by tracking 3 channels around small risks for a week. The external cue you noticed, a wobble in the bike ahead, the bodily change that came with it, a throat pinch, a breath hitch, a warm scalp, and the outcome. Write brief timestamped notes. Patterns will emerge about which bodily whispers map to real hazards for you. Second, train in domains where anticipation is teachable and measurable. Defensive driving classes that emphasize reading mirrors and tire angles. Street awareness courses that drill baseline versus deviation. Sport drills that force you to commit based on the earliest possible cue. These reps shrink the gap between I think something's off and I know what to do. Third, pair intuition with a simple decision protocol so feeling becomes action rather than rumination. In fast situations, use a 3-beat script. Notice, name, nudge, notice, left truck drifts. Name, likely lane change without signal. Nudge, ease off, open space. And in slower ones, use a lightweight checklist. What's the best case? The base case? The red flag that would make me exit. So your alarms land in a structure that respects both speed and sanity. Fourth, lower background noise in your body so true signals stand out. Sleep enough that baseline anxiety doesn't masquerade as foresight. Hydrate and eat so glucose dips don't generate spooky flutters. Practice 1 reliable downshift, 4 slow exhales, or a brief box breathing set, so you can cool an adrenaline spike and separate pattern detected from panic detected. Fifth, inoculate yourself against the mind's 2 biggest traps in this area: hindsight and confirmation. Hindsight sows a clean narrative after the fact. I knew that call would go badly. And empties the learning. Confirmation hunts only the hits. Counter both by keeping a short log of intuition calls with outcomes, including the ones that didn't pan out, and by reviewing them monthly with a friend who will ask, kindly, what did you really know and what did you do because of it? When intuition travels into professional settings, harness it without letting it run the room. Pilots use crew resource management so that a first officer's "I have a bad feeling" always translates into an explicit call. Unstable approach, go around, and a shared plan. ER teams honor a nurse's "this patient looks wrong" by triggering a structured early warning score rather than relying on vibes. In finance, some firms require that gut-based exits be documented with the specific pattern noticed, then backtested later, turning instinct into hypotheses that can be improved. This discipline also protects you from charlatans, because genuine skill produces repeatable cues and clear thresholds, not vague prophecies that flex to fit any outcome. There is a quieter, more intimate version of all this worth naming: relational intuition. In long partnerships and teams, micro-shifts in expression, cadence, and posture telegraph conflict and need. You can feel an argument coming because your history has taught your body the preface. Here, the ethical move is to act early with care. Ask a question, slow the conversation, change the setting, rather than to assume you've read the future. Your early move changes the future, which is the whole point. To round the edges without blunting the lesson, carry two paradoxes out with you. First, the better you get at listening to your body's fast warnings, the more you must invest in guardrails that keep superstition out. Pre-commit to what evidence will make you override a hunch, and put a skeptic in the loop for big, slow, reversible decisions. Second, the more you practice anticipation, the more you must design your world to lower the need for it. Bright bike lights and generous following distances beat any sixth sense. Clear workplace norms beat sensing a blow-up. Cooking mice on place beats smelling smoke. The soft closing keeps the wonder intact without bending physics. There is no need to invoke time running backward when you already live in a mind that runs a little ahead. Your best premonitions are glimpses of the immediate future, assembled from thin slices of the present by a nervous system tuned for survival. If you want more of the ones that help and fewer of the ones that waste adrenaline, train your eye for precursors. Train your body to signal cleanly. Give your feelings a simple path into action. And keep score honestly enough that you refine, not mythologize, the part of you that sometimes knows a second early and uses that second well.